Maths today we're going to go through the whole of differentiation in higher maths. So that is everything in this list. You can see it's quite a comprehensive list, but this video is going to focus on teaching you at least a few questions and techniques for each topic, so full in-depth teaching, but then also it'll go through every single past paper question on differentiation, split into its various sections. Let's just get started straight away. Let's kind of clear maths. Today we're going to be looking at how to differentiate f of x equals x squared. Why is it 2x? Which you should all know from higher maths. So I've drawn the graph of y equals x squared, or f of x equals x squared. And we've got a couple of points here that we can just move around and it gives us a line. We can think of differentiation as like the gradient. So taking these 2 points and showing you that, you can essentially make a triangle here by joining up here. And you should know that the gradient is defined as the vertical distance of a horizontal. So defining our points, this first point I went along x, and then if we put x into the function we get f of x back for our second part of the point. Our second point though, I've went along x plus a little bit, let's call it h. Then that means that our vertical distance would be f of x plus h. So looking at our distances, a distance of h, x plus h minus x is h, and the vertical distance would be f of x plus h minus f of x. So the gradient of this line between these 2 points would just be f of x plus h minus f of x all over h. Now, we don't define differentiation as the gradient of a line between 2 random points on our function. We define it as the gradient of the tangent, in other words, at a particular point. So if we go back to our animation, as these points get closer and closer together, you can see the distance between them becomes nothing essentially, and therefore at h, the distance along the x-axis becomes nothing. As these points get closer and closer together, that distance here, that h becomes very small. In fact, when they're touching, when it is the gradient of the tangent, when it's actually a tangent, h would equal 0. So we've now essentially got a definition for differentiation. Differentiation is a gradient as h goes to 0. So as h becomes 0, approaches 0, the limit as h goes to 0. So in other words, our definition of differentiation is for f of x being a function is f dash x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. Vertical over horizontal, but as h goes to 0 to make it a tangent. And we can use that now to differentiate any function we want. Let's differentiate x squared and see what happens. So differentiating x squared from first principles, then f dash x, remember, is just going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. So plugging in our actual function, which is x squared, we get x plus h squared minus x squared over h. So that is the limit as h goes to 0. We can expand the top to get x squared plus 2xh plus h squared minus x squared all over h. And we're trying to really eliminate this fraction because we can't divide by 0. So that is the limit as h goes to 0. X squareds cancel, so we get 2xh plus h squared over h, which is the limit as h goes to 0. Dividing through by h then, we get 2x plus h. So as h goes to 0 though, that means we'll have 2x plus nothing, which is just equal to 2x. Therefore, if f of x equals x squared, the differential is 2x. Now we can expand that to any function we want. Let's say we had f of x equal to x cubed. Then f dash x would be the limit as h goes to 0 of f of x plus h, so x plus h cubed, minus x cubed f of x all over h. Now you can take your time and expand x plus h cubed if you want, or if you know the binomial theorem or something else to expand it quick, you can. So I'm just going to expand it very quick, and I get the limit as h goes to 0 of x cubed plus 3x squared h plus another 3xh squared this time, plus h cubed, and we've got minus x cubed still on the top. And again, we're trying to eliminate this fraction. So that is the limit as h goes to 0 of x cubes cancel, so we've got 3x squared h plus 3xh squared plus h cubed all over h. We can now divide through by the h to get 3x squared plus 3xh plus h squared. Now there's no fraction, so as h goes to 0, that equals 3x squared plus 3x times nothing plus nothing, which just equals 3x squared. So therefore, if f of x equals x cubed, f dash x equals x squared times 3. Later on in the course, if you're doing advanced higher maths, you'll learn something called the binomial theorem, and using the binomial theorem you can prove that if f of x equals x to the power of n, f dash x is n times x to the n minus 1. But I'm not going to do that in this video. Mr. Cullen here from Current Maths. Today we're going to be looking at differentiation, and we're going to go straight into it with the power rule and all the rules you need to get ready to differentiate a function. So all that manipulation you're going to have to do. If you want to know what differentiation is and where it comes from and how to differentiate from first principles, look at my previous video. Link is up above right now. But for now, we're going to look at what differentiation is in terms of how we actually do it. So it's the rate of change of a function is what differentiation is, or the gradient of the tangent. And usually that's when you've drawn a graph of a function, it's the gradient of the tangent at a specific point. We'll get to that once we get to later examples, but for now let's look at the first main rule, which is called the power rule. If you take a function f of x equal to x to the power of n, and x would be a member of the real numbers usually, then f dash x is just n times x to the n minus 1. In other words, the power has been dropped to the front and we've took 1 away from the power. We're going to use that in a number of scenarios. It looks simple, but sometimes it's not so simple when you have to manipulate the function first. A little bit of notation before we go on though. There's a couple of main notations we use at higher maths. Lagrange notation, that's when the function is something like f of x, then the derivative would be written as f dash x. Now we could have different functions. We could have g of x, and in that case you could have g dash x. And it doesn't have to be x, of course, it could be any letter. We usually use x and y simple because that's the coordinate system we use. And the other one we normally use is called Leibniz notation. So if your function is written as an equation like y equals f of x, then the derivative could be d by dx of f of x, or more commonly, the y by dx is what you'll see. Now, the good thing about d by dx is you can then do the derivative of an expression without calling it f of x or y. For instance, you could have d by dx just meaning differentiation with respect to x. In other words, if a function is in x, to differentiate it so your thing's in x. In other words, d by dx of x cubed would be 3x squared. Take a power down, take away 1. If y was equal to x cubed, then the y by dx would be still 3x squared. Notice the rotation's shifting. Or if f of x was x cubed, then f dash x was 3x squared. And you'll have to know all these different notations and realise that it all means the same thing. Okay, straight on an example. Example 1 says a function f is defined for x as a member of the real numbers by f of x is x to the power of 4. Find f dash x. So f dash x, very, very simple, is I take my 4 down in front, write x again, and I take away 1 from the power, So that leaves me with 3. And we're done. That is it. Example 2 says a function is defined for x as a member of real numbers by f of x is 2x cubed. Find f dash x. Slightly more complicated building this up. So f dash x, well, 2 is just a number. So I take 3 down in front, but I need to then times by 2x. And then the power goes down by 1. 3 minus 1 is 2. So that 2 doesn't go anywhere, it just stays there. So it's 3 times 2. So I tidy that up to get 6x squared. And usually you could probably do that automatically. Let's have a look at some negative and fractional indices. What happens when that happens? So let's example 3 says f of x is x to the power of minus 3. And I've just written in brackets x is a member of real numbers, of course. So we have to find f dash x. Nothing exciting or new here. The power comes down in front, so minus 3x. And we reduce the power by 1. Minus 3 take away 1 is minus 4. Now we can tidy that up slightly by leaving it as a positive power. If you remember your rules of indices, then that would be minus 3 over x to the power of 4. It's perfectly acceptable at higher maths to leave your answer in this form, but often you'll want to go that one step further because sometimes you'll be substituting a number in without a calculator, so you'll need to have it as a positive power. Example 4 says f of x is 4 times x to the minus 2. X is a member of real numbers. Find f dash x. So our function is f of x, f dash x. I take minus 2 down to the front. I'm going to times that by 4x. Minus 2 take away 1 is minus 3. So that equals minus 2 times 4 is minus 8. X to the minus 3. Or if you wanted it as a positive power, that's acceptable, remember. Minus 8 over x cubed. And we're done. Example 5. F of x is defined as x to the power of minus a third. X is a member of real numbers. Find f dash x. Fractional power, no problem there. The power comes down to the front, so it's minus a third x. And I need to take away 1. Minus a third take away 1 is minus 4 thirds. And what you get used to doing with taking away 1 is just take away the denominator. If I'm in thirds, I take away 3 from the numerator. If I'm in quarters, I take away 4. So minus a third, take away 3 thirds is minus 4 thirds. Now let's actually leave this one as a, we could leave it like that and that's perfectly acceptable, remember. But let's actually switch it to what it is as a positive power to start with. So as a positive power, f dash x is going to be minus 1 over 3 x to the 4 thirds. What about, though, what is x to the power of 4 thirds? What if I had to do a number like 2 to the power of 4 thirds? How would I work that out? Well, remember, that changes to a third. So let's do that. F dash x would then equal minus 1 over 3, a root sign, and it's the third cube root of x to the power of 4. So to work that out from National 5 rules of indices, we've got x to the power of 4 just goes straight underneath, and that means the third root, the cube root of it. If it was a 5 here, it would be the fifth root, and if it was a 2, it would be the square root. Okay, and we'd maybe want to do that again if it was a non-calculator, but I wouldn't give myself a headache. I would leave it like that if I was just looking for an answer. Okay, differentiation with more than one term. So quite often you get x cubed, x squared, x, and it's all add or plus. They're quite simple to deal with as well. Example 6 says, find dy by dx when y is 3x cubed minus 2x squared plus 5x. So I've switched to using dy by dx. So I write dy by dx. And I just differentiate each term separately. So dealing with the first term, I get 3 times 3x squared because I take away 1. The second term, take 2 down to the front, so minus 2 times 2x to the power of 1. And the last term, well, it says 5x, there's no power, so I can add a little power 1, and that becomes plus 1 times 5x to the power of, and I'll write 0, but you never will. dy by dx equals 9x squared minus 4x to the power of 1 plus, well, 5. X to the power of 0 is 1. So a term where it's just an x the x just goes away and you're left with just the number, or the power. Well, the power is always going to be 1, so just the number actually in front. And there we go, our final answer. Example 7 says find dy by dx when y equals x minus 3x plus 2. Now do not be tempted to try and differentiate this first. You can't do it because it's a bracket times a bracket. You need to separate it out into its terms, which is term plus term plus term. Otherwise we can't do it, not right now. So we start manipulating y. So y equals, well, we can work this out at the side. It's just multiplying it brackets. I'll use a grid just to be very clear. So if I draw a grid like so, and on one side I put x minus 3, and the other side I put x plus 2, then I get x squared minus 3x plus 2x minus 6, or x squared minus 1x minus 6. So I've now worked out what my y is. X squared minus x minus 6. And you could have multiplied it out any way you wanted, but as long as you've multiplied it out, then you just go straight into dy by dx. That becomes 2x minus x to the power 1, so that's minus 1. And you'll notice we've got a number on the end where there's no x to differentiate. If that was x to the power 0, then it would be 0 times 6, which is 0. So a number just differentiates to nothing, so it goes away. And there's our final answer. Okay, differentiating with maybe surds or indices. Let's have a look at example 8. Differentiate square root of x with respect to x. So I'm wanting to do d by dx. Remember our notation of root x. Well, that's going to be d by dx of, I can't differentiate root x, I don't know. There's no power, I need a power. So the square root of x is x to the power of a half. We change it to a power, and then we can work out our answer. A half comes down to the front, x, a take away 1, a half take away 1, a half take away 2 halves is minus 1 half. That's a perfectly acceptable answer, but I'll try and leave it as a positive power. So we get 1 over 2 x to the half. If you want to go one step further and you want it back as a root, then you would just go 1 over 2 x to the half is the square root of x, and we're done. Example 9 says find the derivative of y equals 1 over x squared with respect to x. So we need to get it ready first. Y equals 1 over x squared. Although there's a power, we've never differentiated anything unless it's x to the power of something only, not a fraction with the x squareds on the bottom. So whenever this happens, you have to remember your rules of indices. At x squared on the bottom becomes x to the minus 2. So now I can differentiate. The y by dx is minus 2x to the minus 3, taking away 1, or leaving your answer as a positive power, minus 2 over x cubed. Example 10. Differentiate y equals 2 over x with respect to x. Again, I can't do anything, so we need to get started with by changing y equals 2 over x to 2x and then a minus 1, because that's like a power of 1. Now I can differentiate. The y by dx, minus 1 times 2 is minus 2x, minus 1 take away 1 is minus 2, or leaving our answer as a positive power, minus 2 over x squared. Example 11 says find the derivative of y equals 1 over 2x with respect to x. Again, y equals 1 over 2x I cannot do anything with because the x is in the bottom of a fraction. So we leave the 1 on top times x to the minus 1, taking it up. The 2 is still on top. Don't be tempted to move that 2. It's just a number. It's a fraction. Fractions are fine as long as they're numbers. Tidying that up, the 1 times something is just something, so it's x to the minus 1 divided by 2. Or you might find it easier to write that as a half of x to the minus 1, so you can see exactly what's happening. So now we've got the y by dx. Minus 1 goes in front. I'm still timesing by a half x to the power of minus 2, take away 1. Tidying that up, minus 1 times a half is minus a half, x to the minus 2, positive power, minus 1 over 2 stays where it is, but the x can join it and become x squared. And we're done. Okay, example 12 says differentiate 3 over 2 root x with respect to x. So we've got to do d by dx of 3 over 2 root x. Well, I can't do that yet, so I'm going to have to tidy that up. So let's get rid of the root first. So that's d by dx of 3 over 2x to the half. That equals d by dx of 3x to the minus a half, taking the x up, over 2, or 3 halves x to the minus a half. Now I can do it, being very careful, that now equals minus a half times 3 over 2 x to the minus 3 halves. Minus a half, take away 2 halves, or 1 is minus 3 halves. Multiplying out our fractions, minus 1 times 3 is minus 3, 2 times 2 is 4. So we get minus 3 over 4 x to the minus 3 halves. And that would be a perfectly acceptable answer. But let's tidy it up and make it all positive. So we've got minus 3 over 4x to the 3 halves to start with. And that equals minus 3 over 4. And it's a root. It's a square root because the denominator of the power is 2 of x cubed. The x cubed goes along for the ride underneath, and then the root is determined by this number, which is a square root. And that would be as done. Example 13. F of x is x over 5 plus 1 over x squared, where x is a member of real numbers. And in this case, we're told that x doesn't equal 0. This is just extra information that we don't actually need, but it lets us define the function because x can't be 0 because we can't divide by 0. We've still to find f dash x. We're going to have to find a way to make this all x's on top of fractions before we can start. So we'll start off manipulating it. So we've got f of x. I'm just going to write that as a fifth of x because it's easier to see what's going on. And then plus x squared becomes 1 times x to the minus 2. If there was another number here except 1, then that number would come along for the right as well. We can now differentiate it. F dash x, that's x to the power 1, remember? So 1 times a fifth is a fifth. That becomes x to the 0. Remember, x on its own, when you differentiate it, the x just disappears because the x to the power 0 is 1. So it's just a fifth. Plus minus 2, so it's minus 2x. Take away 1 is minus 3. Now that's a bit messy, so we can tidy that up by writing it as 1/5 minus 2 over x cubed, and that would be perfectly acceptable. If we wanted to go one step further and leave it as a single fraction, you could, but we're not going to. Example 14. Well, now reach the time where there's a single fraction. What can we do? You've got differentiate x to the 4 minus 3x squared all over 5x. When you've got a bunch of things on top of a fraction separated by a plus and a minus, as long as they're on the top of the numerator, you can separate that into 2 separate fractions and then deal with them and simplify them separately. Can't do that if the denominator's things that are plus and minuses. That's not the same. Okay, so let's start off by saying that we've got x to the 4 minus 3x squared all over 5x. Well, that's going to equal x to the 4 over 5x minus 3x squared over 5x, and we can simplify those fractions. The laws of indices, that's got a power of 1 and 1. So 4 minus 1 is 3. So we get x cubed over 5. 2 minus 1 is 1. So minus 3x to the power 1 over 5. And now our fractions have all got x's on top, so we can immediately just differentiate. So d by dx over our original thing equals 3 comes down, 3x, take away 1 is squared over 5, or 3/5 of x squared if you prefer, minus just 3/5 because x to the power of 1, remember? Now we can tidy that up a little bit because 3/5 is a common factor here. So if we imagine it as 3/5 of a common factor, you're going to have x squared minus 1 if you really wanted to. And we're done there. Example 15, find the derivative of y equals square root of x times x squared plus the cube root of x with respect to x. Again, we're obviously going to have to tidy this up. You can't have brackets that are times by brackets or brackets times by numbers before you do anything. You have to multiply it all out and get it to separate terms. So let's do that. So y equals square root of x. I'm just going to straight away get rid of that x to the half times x squared plus the cube root of x, x to the third. So there's my first step. Let's get rid of all the roots and make them all powers so we can multiply them out easily enough. So y equals, laws of indices, a half plus 2, x to the 5 halves. How do I do that so quick? Well, 2 is 4 halves plus 1 is 5 halves. I'm now going to have to do a half plus a third because I'm adding the powers because of the laws of indices. So maybe at the side, a half plus a third is equal to 3 over 6 plus 2 over 6, which is 5 over 6. So we've now got plus x to the 5 over 6. We can now differentiate it because they're separate terms. So dy by dx, 5 halves goes in front. X. Take away 1 from 5 halves. So take away 2 halves. 5 minus 2 is 3. So I get 3 halves. And the second one, plus 5/6. Take away 1 from 5/6. So take away 6/6. 5 minus 6 is minus 1. 6th. That would be a perfectly acceptable answer, but we can tidy it up. So we will. Let's make it all back into roots. So dy by dx in this case would be 5 square root of x cubed over 2 plus 5 over 6 times, well, it'll be x to the 6th. I'll write that first and then I'll fix that one. So that is 5 square root of x cubed over 2 plus 5 over 6, the 6th root of x. Now, normally you wouldn't have to go that far, but like I said, the only time you have to do that is if you've then got a number to substitute in. But I get in the habit of doing it every single time just for the practice, okay? But if you're in an exam situation, just leave your answer there. Don't go any further. And speaking of an exam situation, 2016 paper 1, question 2 says, given that y equals 12x cubed plus 8 root x, where x is greater than 0, find dy by dx. Okay. Y equals 12x cubed plus 8 square root of x, x to the half. That's our first step, mark 1. The y by dx, I'll read it like 36 because 3 times 12, x squared because take away 1, plus a half times 8 is 4x, and it's to the minus a half. Notice it does not say leave it as a positive power. It doesn't say to substitute a number in later or anything else. There's your final acceptable answer. You don't need to do anything else. But just for the practice, the y by dx would then equal 36x squared plus 4 over x to the half. So that's the square root of x. And that extra step is not required. Differentiation at higher maths, trig functions. We can look at the derivatives of sine and cos and see what we get. It's important to note that the derivatives of sine and cos are only defined when the x-axis is in radians. That is because radians are just a number and you need your axes to be the same, the x and the y, for you to do differentiation. You can't have degrees and then numbers on the side because that's a different measurement. But drawing these graphs just with degrees is our normal way. There's our sine graph there. And there's a cos graph. If you think of the derivative of sine, it's positive to between 0 and 90, and then it drops negative between 90 and 180. So it starts positive, it has to drop to 90 because it goes underneath. But then at 180 again, the sine graph is negative up to 270, So it stays negative, but it turns at 180. So it must be going up to 270 and 180. And you will be looking at graphs of derived functions soon. But all you need to know at higher maths is, if you do differentiate sine x, you get cos x. And similarly, but slightly different, if you differentiate cos x, you get minus sine x. And these are given at the start of the exam paper. And just make sure you're not working in degrees for later questions when you're doing this. But most of the time, the questions will be obviously in numbers and radians anyway. By differentiating trig functions, example 1, differentiate y equals 3 sine x with respect to x. If y equals sine x, then the y by dx is cos x, and that's just from the start of the exam paper. So that's just a little note for myself. I'm just grabbing that from the start of the exam paper. So now it says differentiate y equals 3 sine x. That means that the y by dx for this question is just 3 cos x, and we're done there. Differentiating trig functions, example 2. A function f is defined by f of x as sine x minus 2 cos x. For x a member of real numbers, find f dash x. So just a little note to ourselves, sine goes to cos from the start of the exam paper, and cos goes to minus sine. So you're kind of taking a note of these. Every time you need to differentiate a trig function, you're checking the start of the exam paper. So then we can just differentiate this, f dash x. Looking at the first thing, sine x goes to cos x, minus 2 cos x. Well, cos goes to minus sine, minus 2 times minus sine x, which equals cos x plus 2 sine x. And notice there's no degrees signs on theirs because we're working in radians, which we'll learn about when you do trigonometry. This is Claire here from Claire Maths. Today we're going to be looking at the rates of change in terms of differentiation at higher maths in Scotland. So the derivative of a function describes the rate of change of the function. This can be evaluated using specific values by substituting them into the derivative. So if we know the derivative and we want to find the rate of change at a specific point, say x equals 2, we can just substitute 2 in. Similarly, later on we'll see that we can also do that with the gradient of the tangent, which means the same thing as the rate of change. Let's look at some examples. Okay, so the first example says, given that f of x is 2x to the power of 5 for x a member of real, find the rate of change when x equals 3. So this is nice and simple to start with. We can straight away say f of x is 2x to the 5. We need to differentiate it to find the rate of change. So f dash x is 10x to the 4. When f dash 3 then, so f dash 3 equals 10 times 3 to the power of 4. So we need to work out 10 times 3 to the power of 4. You can use the calculator for that. 3 times 3 is 9, times 3 is 27, times 3 is 81, times an extra 10 makes 810. So our rate of change is 810 at x equal to 3. Let's look at this in some context then, looking at the context of displacement, acceleration, and velocity. Velocity is the rate of change of displacement with respect to time. So in other words, if I wanted to write that as a formula, velocity would equal ds by dt, or in other words, v of t would equal s dash of t, right? Same with acceleration. Acceleration we define as the rate of change of velocity with respect to time. It's how velocity changes over time. So acceleration must be dv by dt, or a of t is v dash of t. And we can do some examples where we need to work out velocity or we need to work out acceleration. And you'll need to know what that means to differentiate, because this is to find the rate of change. A ball is thrown so that its displacement, s meters after t seconds, is given by this formula. S of t is 12t minus 5t squared. We have to find the velocity after 2 seconds. So we know that the velocity with respect to time is equal to differentiating the displacement with respect to time. So the velocity is just equal to, if I differentiate this function, 12 minus 10t. And we want it after 2 seconds, so we can substitute 2 into this. So v of 2 is equal to 12 minus 10 times 2. That's 12 minus 20, which is minus 8. And since we've been given units in our question, we give units in our answers, so that's meters per second. Example 3, the value of an investment is calculated using the formula V of t is the square root of t cubed, where V is the value of an investment and t is the time in years. We have to calculate the growth rate, and it tells us that means the rate of change of the investment after 9 years. So it mentions the rate of change, so we need to differentiate our formula. So V of t is equal to the square root of t cubed. Need to get that ready to differentiate, so that means it's t to the power of 3/2. So v dash is equal to 3 over 2 t to the half, taking away 1. And we want that after 9 years, so we can just substitute 9 into this. So it's v dash of 9 is 3 over 2 times 9 to the power of a half. Now let's just assume we're doing non-calculator. So that's 3 over 2 times the square root of 9, which is 3 over 2 times 3, which is 9 over 2. So the value of our investment after 9 years is 9 over 2. That's what we're going to look at today. Is going to start looking at the gradient of a tangent to a curve. If I draw a curve here, we know that we can find the gradient at a specific point, and that gives us, we could draw a tangent, a line that just touches that point. The gradient then would be the same as the rate of change. It changes by, go along x, y changes by some number. If we go for every x, y changes. So at a specific point, we can find the gradient or at the point or the gradient of the tangent, which is the same as finding the rate of change. So if we differentiate, we find the gradient of the tangent. If given a point, we know the gradient of the tangent or the rate of change at that point. Example 4 then says, find the gradient of the tangent of the curve with equation y equals 3x squared at the point 5, 2. So we know that y equals 3x squared. We've got that power word, gradient of the tangent. So we do the y by dx, which is equal to 6x. And then we know the point's 5, 2. So at x equal to 5, the y by dx equals 6 times 5, which is 30. So our gradient is equal to 30 at the point x equal to 5. Mr. Coyle here for Coyle Maths. Today we're going to be looking at equations of tangents to curves for higher maths at differentiation. So you should remember that the first thing is differentiation tells us the gradient of the tangent of a curve. So if I draw a curve like so, a tangent, remember, is just a line that touches it at one point, and if we differentiate a function, we're given an equation that would tell us the gradient. And if we had a specific point, then we could substitute that point in to find the specific gradient and then use y minus b equals mx minus a to find the equation of the tangent. So example 1 says, find the equation of the tangent to the curve with equation y equals x squared minus 3 at the point 2, 1. So our first step is to differentiate this function to find the equation for the gradient. So the y by dx is just equal to 2x. So at x equal to 2, our gradient equals 2 times 2, which is 4. So we've got our gradient. Now we can use y minus b equals mx minus a. So our point, remember, is 2, 1. So that is an a and a b. So y minus 1 equals 4, the gradient, x minus 2. And we can just multiply that out to get y minus 1 is 4x minus 8, or y equals 4x minus 7. There's the equation of our tangent at the point 2, 1. A function is defined on a suitable domain by f of x is x cubed minus 2x. Find the gradient of the tangent to the curve y equals f of x at x equal to minus 2. Notice we're only given the x part, so we're going to have to find the y part of the coordinate at some point as well. So let's start off by finding our gradient. So same steps, f dash x is equal to 3x squared minus 2. At x equal to minus 2, we can substitute that in. F dash of minus 2 equals 3 times minus 2 squared, take away 2. That's 3 times 4 minus 2. That's 12 minus 2, which is 10. So we can state that our gradient is equal to 10. We now need a y part of our coordinate, so we can substitute that into f of x, because y equals f of x. So if I do that at the side, remember, y equals f of x, which is x cubed minus 2x. So f of minus 2 equals minus 2 cubed minus 2 times minus 2. Minus 2 cubed is minus 8. Minus 2 squared is 4. Minus 8 add 4 is minus 4. So our point is simply minus 2 minus 4. And that's going to be our A and B. So we can now use y minus b equals mx minus a. So we've got y minus minus 4 equals 10x minus minus 2. So y plus 4 is equal to 10x. Multiplied out the bracket gives us plus 20. Or y equals 10x. 20 take away 4 is 16, so plus 16. The equation of our tangent is y equals 10x plus 16. Okay, final example before we move on to past paper questions. Example 3 says, find the equation of the tangent to the curve with equation y equals the cube root of x squared, where x is negative 8. So we're going to have to differentiate it, so we need to get it ready to differentiate first. So y equals not the cube root of x squared, but x to the power of 2/3, using the laws of indices. So the y by dx is 2/3 of x, take away 1, I get minus 1/3, or to tidy that up, 2 over 3 times the cube root of x. So at x equal to minus 8, our gradient equals 2 over 3 times the cube root of minus 8. This could be a non-calculated question, which is why I put it back as a third, because the cube root of minus 8 is minus 2. So we get 2 over 3 times minus 2. And simplifying that gives us minus 1/3. So we've got our gradient is minus 1/3. We now need to find our point, remember, as well. So we need to substitute into y. So going back up, remember y was equal to the cube root of x squared. So at x equal to minus 8, y equals the cube root of minus 8 squared. Cube root of minus 8 is minus 2, so that equals minus 2 squared, which is 4. So our point is simply minus 8 and 4. And now we're almost finished. We've got our point, we've got our gradient, so we can use y minus b equals mx minus a. So using y minus b equals mx minus a, there's our a and b. We've got y minus 4 is minus 1/3, x minus minus 8. Tidying that up by eliminating the fraction, I'll just multiply through by 3. We get 3y minus 12 equals minus 1x plus 8. Or 3y minus 12 is minus 8. Take away 8. So 3y plus x equals, taking the minus 12 across, 12 take away 8 is 4. That's one way you could leave it, or you could leave it as y equals minus 1/3 x plus 4/3 as well, if you just kept it as a fraction. 2015 paper 1 question 2 says, find the equation of the tangent to the curve y equals 2x cubed plus 3, where x is minus 2. So the first thing we need to do is differentiate that. So dy by dx is equal to 6x squared. So at x equal to minus 2, our gradient equals 6 times minus 2 squared. That is 6 times 4, which is 24. We've now got our gradient, but we're near a point. So getting our point, y equals 2x cubed plus 3. So at x equal to minus 2, y equals 2 times minus 2 cubed plus 3. That's 2 times minus 8, add 3. That's minus 16, add 3, which is minus 13. So our point is just minus 2 minus 13. So we've now got our point, so we now can just work out the equation of the tangent by using y minus b equals mx minus a, if you like. So there's our a and b. So y minus minus 13 equals 24, x minus minus 2. So we can change that to y plus 13 equals 24, x plus 2. And for the purpose of the SQA, you would get your mark, your fourth mark finally at that point anyway. But let's just multiply it out and get the form we like usually. So y equals 24x. You get 48, take away 13, which is 35, so plus 35. And we're done for our fourth mark. Okay, 2018, paper 1, question 7, quite a long one this. Write down the coordinates of P. It gives us a curve with an equation, it gives us a line. It says write down the coordinates of P when it cuts the y-axis. So there it is there. Well, that's quite easy. It cuts the y-axis when x equals 0. So if I just substitute 0 into this equation, I get 0, 0, 0, 5. So it says write down, it just wants me to write down 0, 5. And there's no real working required for that to do that. Okay, part B says, determine the equation of a tangent to the curve at P. So we've got our curve's equation, we've defined the equation of a tangent, so we need to differentiate it and do exactly what we've been doing before. So part B, dy by dx equals 3x squared minus 2 times 3 is 6, so 6x plus 2. So we've got our differentiated equation, that tells us the gradient, and it's at the point P, and P, remember, was 0, 5, so at x equal to 0, the y by dx just equals 2. So our gradient equals 2. Our point, remember, is 0, 5. So therefore, we can work out the equation straight away. I know it's 2x add 5 because if it cuts the y-axis, c is 5. But if you prefer to use the same method straight away, you can just call that a and b and do y minus 5 equals 2x minus 0. So y equals 2x plus 5. And that is the equation of our tangent. Part C is quite commonly find the coordinates of Q where the point meets the tangent again. It's talking about meeting or intersections, so that means that it is simultaneous equations, okay? It's the point where the line's equation equals the curve's equation. So let's do that for part C. So our curve's equation is x cubed minus 3x squared plus 2x plus 5. X cubed minus 3x squared plus 2x plus 5. And our line's equation is 2x plus 5. And therefore, the point of intersection we can say that x cubed minus 3x squared plus 2x plus 5 equals 2x plus 5, because the y of the curve must equal the y line. Let's rearrange that then. So we can see there's 2x on both sides, so they cancel, 5 on both sides cancel. So you end up with just x cubed minus 3x squared equals 0. And we can solve that by factorising. X squared is a common factor, so we've got x minus 3 equals 0. So x equals 0 or x equals 3. Now we've already used the 0 part, so we need to use the 3 to get our y. So using any of the y equations, might as well just use the simplest one. At x equal to 3, y equals 2x plus 5, so that's 2 times 3 plus 5, which is 11. And we need to then state the actual coordinate. So our coordinate is 3, 11. 3, 11 is our point, and we're done. Mr. Clare here from Clare on Maths. Today we're going to be looking at increasing, decreasing functions for higher mathematics differentiation. So just to remember, for any function f of x, to work out the gradient m, we can differentiate it f dash x. Now, if the derivative is greater than 0, it means that we have a positive derivative. It means the function is increasing. If the derivative is 0, it means we've got a stationary point. In other words, we've got a turning point. The function is stationary. And finally, if we get a negative derivative, if the derivative is less than 0, it means the function is going down the way, it's decreasing. And we can use that fact to find out whether a function is increasing or decreasing at a given point or through a range of values, or we can later on find it using to find stationary points. So here's a picture that kind of illustrates this point. Let's say we had a function like so. The derivative dy by dx is greater than 0 going up this way, so the function is increasing. It then hits a stationary point. It then drops back down. The derivative will be negative because the gradient of the tangent will be negative. It is then 0, and then the derivative rises back up. The gradient of the tangent is greater than 0. Okay, example 1 says state whether f of x equals 2x cubed minus 3x plus 3 is increasing, decreasing, or stationary at x equal to 2. So first thing we can do is work out our derivative, f dash x. F dash x is 3 times 2 is 6x squared, taking away 1, minus 3, and the plus 3 goes to 0. So all we need to work out is substituting 2 in to see if that is positive, negative, or 0. So that's 6 times 2 squared minus 3, 6 times 4 minus 3, 24 minus 3, which is equal to 21. F dash 2 is positive, I should say is, therefore f of x is increasing at x equal to 2. Example 2 says, show that the function f of x equals x cubed minus 3x squared plus 3x minus 10 is never decreasing. This is quite a common question. We need to be very careful with this one. So let's start off by differentiating it and see what happens. So f dash x is equal to 3x squared minus 6x plus 3. And we somehow need to show that that's always positive. Well, one of the things that I know is always positive is a square. If you square something, x times x is x squared. A negative thing is a negative positive. So if I can show that this is somehow a square, perfect square, then I can show that it's never decreasing and therefore always increasing, or at least 0. So let's just try and manipulate this. Taking 3 out as a common factor, we get x squared minus 2x plus 1. Factorising that, we get 3x and x, 1 and 1, minus 1 and minus 1. Well, that's 3 times x minus 1 squared. That's 3 times a square number, which is always greater than or equal to 0, and therefore f of x is never decreasing. So since we managed to make that a square number, we can just say that straight away because it's a given. Okay, example 3 says, similarly, show that the curve with equation y equals 5 minus 4x minus x cubed is always decreasing. So we want to show it's always negative. Let's start by working on dy by dx then to find out if it's positive or negative. So the first term disappears, we get minus 4, and we get minus 3x squared. And we somehow need to show that that is always less than 0. Well, that's quite easy to show. If I just annotate this, that's always negative. When you square a number, that's positive, but then you times it by a negative number, so that's always negative. So you end up with, that means that that is always less than 0. And we're done. So therefore, y equal to 5 minus 4x minus x cubed is always decreasing. Example 4. For what values of x is f of x equal to x cubed minus x squared minus x plus 7 decreasing? So we need to work out the derivative. F dash x is equal to 3x squared minus 2x minus 1. And I suppose what we're wanting to know is when's that decreasing? So we want to know when is 3x squared minus 2x minus 1 less than 0. So we've got a quadratic inequality to solve. So let's work on that. Let's see if we can factorise it. We get 3x plus 1 and we get x minus 1. So at the side we can say that we're solving that equation 3x plus 1 to find the turning points, x minus 1 equals 0, and therefore x equals minus a third and x equals 1 would be our roots. So we know our roots, so we can just draw a picture to work out when that's less than 0 or more than 0. If I draw a quick sketch, y and x, let's call that minus a third, and let's call that 1 over here. That'll be roughly what our picture looks like, and we should be able to see that that's negative or less than 0 only under this point. So between these 2 points it's negative. So for solving our inequality, we can say that minus a third is less than x, which is less than 1. Mr. Clellan here from Clellan Maths. Today we're going to look at differentiation and look at stationary points and how we can tell the nature of those stationary points. So if we look at this picture here, I've drawn a curve in red, and you can see that these are the stationary points, or otherwise known as the turning points, and it's when the graph turns. Now at this point, if you were to draw a tangent, the gradient of that tangent would be 0, it would be a straight line across. So if the gradient of the tangent is 0, it means you've found a stationary point. Let's look just before the stationary point. If this curve is going up the way, the gradient of the tangent at this point would be positive. So if you find the gradient of the tangent is positive, it means this curve is increasing. If you find the gradient of the tangent being negative, it means the curve is decreasing. So you can then look to see just before and after the stationary points whether they're increasing both times, decreasing both times, or increasing and decreasing. And there's going to be 4 options, I suppose. The first option is it decreases, goes to 0, then increases, which means you get a minimum turning point. If the gradient of the tangent increases, goes to 0, then decreases, you get a maximum turning point. But then there's 2 other options. It could increase, stop briefly at 0, then increase again. That's called a rising point of inflection. If it decreases, stops again, and then the gradient of the tangent decreases, it's a falling point of inflection. Example 1 says a curve has equation y equals x cubed minus 6x squared plus 9x take away 4. Find the stationary points on the curve and determine their nature. So the first thing we need to realise is that stationary points occur, and we need to write this when the gradient of the tangent, well, that's dy by dx, equals 0. So dy by dx is equal to 3x squared minus 12x plus 9, and we can say that that equals 0. So we need to solve this equation to find our stationary points. So we can take out 3 as a common factor and get x squared minus 4x plus 3 equals 0. That's going to be double brackets because it's a quadratic. It's going to be 3 and 1, and they're both going to be negative. So that means that x equals 1 or x equals 3. We've found the x part of the stationary point, but we need to find the y part, so we substitute it back into y. X cubed minus 6x squared plus 9x take away 4. So at x equal to 1, y equals 1 cubed minus 6 times 1 squared plus 9 times 1 minus 4. And you can just get a calculator to work that out if you want, and you will realise that the answer is 0. Similarly, when x equals 3, y equals 3 cubed minus 6 times 3 squared plus 9 times 3, and then finally take away 4. If we substitute all that in, x equal to 3, y is equal to negative 4. So we've now got our 2 stationary points. The first one is equal to 1, 0, and the second one is equal to 3 minus 4. But we're not finished there, because we don't know whether they're maximums or minimums or points of inflection. So the easiest way to work that out is a nature table. And essentially what you're going to do is you're going to draw a little table for yourself, x, and you're going to check what dy by dx is at various points round about the stationary points. So our first stationary point for x, it goes along and then it hits 1. and then it continues on its journey. So if we check before 1 and after 1, we'll be able to get the nature of that stationary point. Similarly, if I draw a dotted line, our next turning point, it goes along to 3 and then it continues on its journey. Now, notice I've done a dotted line and done it as if it's 2 separate stationary points. That's just in case the function is discontinuous, which does not happen very, very often at higher, but it's always worth doing that, because if you just draw one arrow here and the function is discontinuous, you may lose a mark. So let's move on. Our dy by dx, remember, is 3x squared. I'll just draw that under here. And then it's minus 12x plus 9. And I suppose we could write shape here to work out what kind of shape it makes. So you're just picking any point you want, so let's just pick 0 for the sake of argument. If I put 0 into this, I get 0, 0 plus 9. That's just positive, so that's sloping up. We already know it's 0 at 1, so it's sloping along. So a number after 1, let's just try 2 for the sake of argument. 2 squared is 4 times 3 is 12, minus 12 times 2 is minus 24, plus 9, that's a negative number, so we're sloping back down the way. So we've got a max for this one. And we can do the same on the other side. So we've already tried 2, so we already know what happens here. We already know that that's negative. We already know that's 0, so we've got going down, going along. So the last number to try maybe is 4 or 10, whatever number's easy for you. I'm going to try 4. 4 fours is 16. 16 times 3 is 48. 48 minus 12 times 4, well 12 times 4 is also 48, plus 9, that's a positive number. So we're sloping back up, that's a min. So we then need to write a little statement. Our turning points, remember, 1, 0 and 3 minus 4. So 1, 0 is a maximum turning point. And 3 minus 4 is a minimum. Turning point. Example 2 says find the stationary points of y equals 4x cubed minus 2x to the power of 4 and determine their nature. So once again we can say that stationary points occur when dy by dx equals 0. We need to write that statement. I've been a little bit lazy by writing xp instead of stationary points. So dy by dx is equal to 4 times 3 is 12x squared, 2 times 4 is 8x cubed, that equals 0. So in this case we can look for a common factor. Between 12 and 8 the common factor is 4, and we've got x squared, so we get 3 minus 2x equals 0. So that means that 4x squared equals 0, or 3 minus 2x equals 0. So x must be 0, or 2x equals 3, which means x is 3 over 2. Or if you're using a calculator, maybe 1.5, but I'll keep it in fractions for this example. So we need to substitute that back into our y, remember. So at x equal to 0, remember our y was equal to 4x cubed minus 2x to the 4. That equals 4 times 0 cubed minus 2 times 0 to the 4 equals 0. So our stationary point is equal to 0, 0. And then at x equal to 3 over 2, y equals 4 times 3 over 2 cubed minus 2 times 3 over 2 to the 4. And if you work that out, you get 27 over 8. So that means that the stationary point is 3 over 2 and 27 over 8. Do not be tempted to stop here. We still need to check the nature of the stationary points. So for the nature, we do our nature table. So we've got x, we go along and hit 0 first, and then we go along, and then our next one is we go along and we hit 3 over 2, and then we go along. So we've got our dy by dx, which, just to remind you, is equal to 12x squared minus 8x cubed. And then that gives us our shape. So picking a number close to 0, let's pick minus 1. Minus 1 squared is 1 times 12 is 12. Minus 1 cubed is minus 1 times minus 8 is plus 8. 12 plus 8 is positive, it's 20. So we've got a positive answer here, which means the shape is going up the way. At 0 we know it's 0, which means it's going along the way. And a number between 0 and 3 over 2, we could just pick 1. So if we just picked 1, we'll get 12 minus 8, which is also positive. So it's going back up, a rising point of inflection. And similarly, looking at the other side, picking 1 again, we get a positive answer. 0 at 3 over 2, and then a number after 3 halves, maybe try 2. 2 2s is 4, 4 12s is 48. 2 cubed is 8, 8 8s is 64. 48 minus 64 is clearly a negative answer. So negative is sloping down the way. So that's a maximum turning point. So now we write a statement about what each turning point is. We've got 0 0 is a rising point of inflection. And we have got 3 over 2, 27 over 8 is a maximum turning point. And we're done there. 2016, paper 1, question 9. Part A, find the x coordinates of the stationary points on the graph of equation y equals f of x and determine when it is strictly increasing. So stationary points, part A. So stationary points, part A. Stationary points occur when f dash x equals 0. So we need to write f dash x. F dash x is equal to 3x squared plus 6x minus 24. We get a mark if we get one of those terms correct. So maybe just the 3x squared, you get a mark. Your second mark is for writing your statement and writing 3x squared plus 6x minus 24 equals 0. So there's mark 2 out of 4. And then we go on to solve that to get our third mark. So we factorise for a third mark and then solve it for a fourth mark. So factorising it, 3 is a common factor, so it's x squared plus 2x minus 8 is 0. That's 3, x and x. And then you're going to have plus 4 take away 2 equals 0. So there is your third mark for factorising. And then your final mark, x equals minus 4 and x equals 2. So we've got x. So we're going to go along to some number minus 4 and then along. And then we've got our second one. We're going to go along to 2 and then along. And then we've got our f dash x. And we know our f dash x is equal to 3x squared plus 6x minus 24. And then we're going to look at our shape. So picking a number before minus 4, maybe minus 5. Now if you use the factorised version, it's easy to see. Minus 5 add 4 is negative. Minus 5 take away 2 is also negative. A minus times a minus is a plus. So that is positive. We know that's 0. And looking at a number between minus 4 and 2, so we could try any number. But let's just try 0. You get 4 times minus 2 is minus 8, so that's negative. So it's sloping down the way. So we already know that this is negative. We already know it's sloping down the way. We know that's 0. And a number after 2, let's try 3. 3 plus 4 is positive. 3 minus 2 is also positive. A positive times a positive is a positive number. So we end up with our slope there. So at this point we get a mark for attempting to draw a nature table, and then for processing this we can then say, since that's a max, that's a min, but we don't have to remember, right, that it's a max or min turning point. It asks us for what values is it increasing. So don't be tempted just to write, oh well, -4 is a max and 2 is a minimum. We're looking now at where is it increasing. Well, it was increasing before -4, so we can write increasing when x is less than -4, or when else is it increasing? Well, it's along, it's decreasing, it's 0, it's increasing again after 2. X is bigger than 2 for our final mark. 2018, Paper 2, Question 9. A sector with a particular fixed area has a radius x. The perimeter is given by this formula. Find the minimum value of p. Again, clue is minimum, so therefore we can say that stationary points occur when, and this will be p dash equals 0, just simply because the function is a function of p. Okay, let's get this ready to differentiate then. So p equals 2x plus 128x to the -1. There you go for 1 mark there. Differentiate it. So p dash is equal to 2 minus 128x to the -2, which is 2 minus 128 over x squared. Second mark there, making it equal to 0 is your third mark. We've already made the statement. So 2 minus 128 over x squared equals nothing is your third mark out of 6 so far. And then we need to go on and solve this. So, solving this equation, we can say that 128 over x squared equals 2, which implies that 2x squared is 128. So x squared is equal to 128 divided by 2, which is 8. X squared equals 128 divided by 2, which is 64. So x equals 8 or x equals -8. A mark if you got x equals 8. Now, you actually don't need the -8 in this case, because if we go back to the original question, remember this is an area. If we pick -8 as our answer, we get a negative answer for our perimeter, which does not make sense in the context of the question. So we could immediately disregard -8. But let's say we didn't, and we just are remembering we need to do a nature table. Then do your nature table for both stationary points, and then pick the correct one. Then we've got x, p dash x, shape. So we're going to go along to -8 and then move all away from -8. Now this is where you need to be very careful. You can't then just put 8 here. This is this one occasion that I talked about earlier where the function is discontinuous. What does that mean? It means at x equal to 0, we don't know what happens because you can't divide by 0. So we need to show that by doing it as either two separate nature tables or just draw a line and then go along, A and along, and that's you covered. Okay? So p dash x, remember, was 2 minus 128 over x squared. So before -8, let's try 10. 10 tens are 100. 128 over 100 is less than 2. So that is positive. It's going up. It's 0. It's going along. After -8, but before we get to 0, let's try, say, 7. Squared is 49. 128 over 49 is more than 2. So that's negative. That's sloping down. And then we need to try a number close to this one. So looking at a number like 7 again, 7 sevens is 49, that is less than 2, so that is negative, that's sloping down, that's 0, is sloping along, and after that we've got 10 tens are 100, that is less than 2, so that is positive, is sloping up. When I said less than 2, I meant more than 2 at this point here. Do apologise for that. And we can then say that that is a max and that is a min. So we can say the minimum value of P occurs when x equals 8. So we need to work out the minimum value of P. So we've said minimum value of P occurs when x equals 8. So remember P was equal to 2x plus 128 over x. So that equals 2 times 8 plus 128 over 8, which is equal to 32. So we've got our final mark occurring here, and we've got a mark for verifying it was a minimum. So there's 1, 2, 3, 4, 5, 6 marks in total. Maths looking at a little bit at curve sketching, because sometimes you need to draw curves of things. So let's look at this graph here. We've got sketch a graph of y equals 2x cubed minus 3x squared. Now, if you remember from National 5, you need a few things when you're doing curve sketching. You need to find the turning points, you need to find the roots, and often you need to find where to cut the y-axis or maybe even the x-axis. So I've taken note of 3 bullet points there. Now, to do turning points, it's stationary points. So that's when they occur when the derivative is 0. So straight away for our stationary point, bullet point, we can say that stationary points occur when dy by dx equals 0. So we can work out our stationary points. So dy by dx is equal to 3 times 2 is 6x squared, and then 2 times 3 is 6 as well, but it's just x. So we're saying 6x squared minus 6x equals 0 for our stationary points. Simple factorization there. 6x is a common factor, so that gives me x minus 1 equals 0. So that means that 6x equals 0 or x minus 1 equals 0. And therefore we can then say that x equals 0 or x equals 1. So we've now got our stationary points, our x value, but we need a y value for a point. So remember, y was 2x cubed minus 3x squared. So when x equals 0, y equals 2x cubed minus 3x squared. So that equals 2 times 0 cubed minus 3 times 0 squared. Should be obvious to see that that is just 0. 2 nothings is nothing, minus 3 nothings is nothing. So we get a point 0, 0. Now we can look at our other point, which is when x equals 1. So when x equals 1, y equals 2 times 1 cubed minus 3 times 1 squared. That is 2 times 1, which is 2, minus 3 times 1, which is 3, which is minus 1. So our point is 1 minus 1. But how do we know if the turning point is a maximum, a minimum, or a point of inflection? Well, that's when we look at the nature of the turning point. So the nature of our turning point, we can draw something called a nature table for this. So a reminder of how that works, if I do it underneath, we've got x, we've got our derivative, and then we're looking at the shape that that makes. So we've went to 0 and 1. So we're going along, hitting 0 at some point and going along. There's our first one. And then we can think of our second one as going along, hitting 1 and going along. And notice I do it as 2 separate turning points. And that's just in case the odd time when the function's undefined between 0 and 1 at some point. So just to be safe there. So we know that dy by dx is 0 at x equals to 0 and x equal to 1. And we just need to examine, well, what happens when it's below 0 and above 0. So if we just pick a number randomly for dy by dx, remember dy by dx is 6x squared minus 6x. Remember dy, I'll just write that here, dy by dx, 6x squared minus 6x, or factorized form 6x, x minus 1. So if you just pick a random number below 0, you can see if it's positive or negative. So I'm going to pick, if I pick minus 1, I get minus 6. Times minus 2, that's positive. So I can say that the derivative before 0 is positive. A number between 0 and 1, let's pick, say, a half, just for the sake of argument, but you can pick any number that works for you. So if you think of a half, I'm just thinking of this. I'm thinking of what, I don't need to work out exactly. A half minus 1, well, I'm just thinking that's negative. And then 6 times a half is positive. A positive times a negative is a negative. So that's negative We obviously know it's negative there as well because it's the same one I've picked. We have a number bigger than 1. Let's pick 2. 6 2s is 12 here. 2 minus 1 is 1. 12 times 1 is positive. It's 12, isn't it? So we can say it's positive. So then the shape obviously goes along, up, along, down. And then for the second one, down, along, up. So we can say that our turning point, 0, 0 it was, is a max turning point, and 1 minus 1 is a min turning point. So we've now got our turning points, that's the main thing, and therefore the next thing we need to do is find our roots. So the roots are where it cuts the y-axis and cuts the x-axis. So looking at the roots, remember the original function was y is equal to 2x cubed minus 3x squared. So it cuts the x-axis, remember when y equals 0. So we just make 2x cubed minus 3x squared equal to 0, and we solve that equation. So we've got a common factor of x squared, so that gives me 2x minus 3. So that means that x squared equals 0, or 2x minus 3 equals 0. So that means that x is equal to 0, obviously, 0 times 0, or 2x equals 3, so x equals 3 halves. So we've got our roots at 3 halves and 0, 0. And then what about cutting the y-axis? Well, that's even easier. That's when x equals 0. So we've got y equals 2 times 0 cubed, 2x cubed, minus 3 times 0 squared. Well, 2 nothings is nothing, 3 nothings is nothing. So that's 0. So it cuts the y-axis at 0, 0, which we already know from the turning point anyway, but that was just a quick check. And we've done everything. We've done our roots, we've done our turning points, we've done our y-intercept. So we've now got enough to draw the graph. So we just draw a quick sketch, x and y-axis, noting our points, which I'll use a different colour for. So we've got 0, 0, we have got 3 halves 0, let's just call that there. So let's say that's 3 halves and that's 0. And then we've got a minimum at 1 minus 1, where 1's going to be before 3 halves. So 1 minus 1 might be about here. And it was a cubic, something like, there's a max, a minimum, and then it goes on. So there's your graph of y is equal to 2x cubed minus 3x squared. And we're done there. Now, later on you'll do a topic, or you might have already done it on polynomials. When you do polynomials, and you'll often do cubics, you will be able to solve a number of cubics. I gave you a simple one here, not having to use the knowledge of polynomials, but later on you'll do other maths to be able to work out the roots for any cubic. It means you can draw the graph of any cubic using that plus differentiation. Okay, let's look at maximum and minimum values. So if we've got any curve, we can find the max and minimums. And usually or sometimes we have the turning points, but other times it just kind of goes on forever. So like for a curve like this, the minimum value is at minus infinity and the max is positive infinity. But if we were to curtail our range and say, look, we want the maximum and minimum value between two certain points on the graph, then the max and the min could either be a turning point, or it could be just the end of the graph, the end where we're touching that line, because there's a turning point there, that's kind of going to go on forever. But so in a closed interval where you're defining an x here and here and saying, look, we want the maximum and minimum between these 2 points, well, either 2 things are going to happen. If you're going to have a turning point, that turning point might be your max because it's turning around, going down, and then it might never come back up, it might come up a little bit, or there might not be a turning point, or it might be a bit below it, and the bit below it would be where the end of the interval is. That would be your max and min. So when you're working at the maximum and minimum values of a function between 2 certain points, you just need to check, is the turning point the maximum and minimum, or is it at the end of these intervals? So let's look at some examples like that. So maximum and minimum points, let's say we had, find the maximum and minimum values of y equals 4x cubed minus 4x minus x squared minus 4x plus 1. In the closed interval, minus 2 is less than 2x less than 2. We just need to check 2 and minus 2, but then check the turning point, okay, of a stationary point. So stationary points occur, you always need to write this statement when dy by dx equals 0. So dy by dx is equal to 3 times 4 is 12x squared, 2 minus 2x, and then minus 4. And we're going to make that equal to 0. So we factorise it, so we can take 2 out as a common factor. 2 sixes, so it's 6x squared minus 1x, and minus 2 equals 0. And then there's a number of methods for factorising. Check my National 5 videos on that. But just by inspection, we should know that the last points are going to be 2 and 1. And the first points should be 6 and 1 or 3 and 2. So we'll just check combinations. You can do a method for checking these combinations. If I tried 6, I would get 6 2s is 12 minus 1. Well, that's not 1. And if I tried 1, I would get 1 2s is 2 minus 6, which is not 1. So I know it's 3 and 2. 3 2s is 6 minus 2. Well, that's not 1. 2 2s is 4, and then 3. So I know it's 2 and 3. And that was just quickly in my head. So I've got 2x and 3x. And then just getting our signs. It's a minus x, so it's minus 2 here to make minus 4x, plus the 3x to make minus 1x. So that means that 2x plus 1 equals 0, or 3x minus 2 equals 0. So our stationary points are x equals minus a half, or x equals 2/3. So our max and minimum values could occur at minus a half, 2/3, or 2 and minus 2. So we'll just check them all. Y equals 4x cubed minus x squared minus 4x plus 1. And we're going to check these 2 points in minus 2 and 2. So at x equal to minus 2, y equals 4 times minus 2 cubed minus minus 2 squared minus 4 times minus 2 plus 1. 2 2s are 4 times 2 is 8. 8 4s is 32, so you get minus 32. 2 2s is 4, but that's a positive with a minus, so that's minus 4. Minus 4 times minus 2 is plus 8, and then plus 1. So doing a bit of maths, you get minus 36 plus 8 is minus 28, plus 1 is minus 27. So there's our first one. Second one, x equal to 2. So y would equal 4 times 2 cubed minus 2 squared minus 4 times 2 plus 1. Well, 2 cubed is 8, 4s is 32, 2 squared is 4, 4 2s is minus 8 plus 1. 32 minus 4 minus 8 plus 1 is 21. When x equals minus a half, we've got y equals 4 times minus a half cubed minus minus a half squared minus 4 times minus a half plus 1. Minus a half cubed is minus an eighth times 4, so that's minus a half. Take your time on that one. Minus a half squared is a quarter, so that's minus a quarter. A half of 4 is 2, a minus times a minus is a plus, plus 2 plus 1. So that is equal to minus a half is minus 2 quarters, minus a quarter is minus 3 quarters, plus 3. Or we can change that to 3 minus 3 quarters is 2 1/4. 2 1/4, or 2 4s is 8 plus 1 is 9 quarters. Clearly 2 1/4 or 9 quarters is not a maximum in, because 21 and 20 is minus 27 beat it. Now checking our last one, x equals to 2/3 was the other turning point. So y equals 4 times 2/3 cubed minus 2/3 squared minus 4 times 2/3 plus 1. 2 2s are 4 times 2 is 8. So that's 4 times 8 over 3 3s are 9 times 3 is 27. 2 2s are 4 and 3 3s are 9. 4 2s are 8 over 3 plus 1. So a bit of work to do here. So that gives us 4 8s is 32 over 27. And then over 27 for the next one, that's times it by 3. So that gives me 12 over 27 for the next one. Well, 3 9s is 27, so I do 9 8s is 72. And then plus 1, which is 27 over 27. 32 minus 12 is 20. 20 minus 72 is minus 52. Minus 52 plus 27, well, minus 25 over 27. which again, you could maybe use a calculator or just take your time on these, but clearly that is neither a max or a min. Then we just pick our max and min values. So going way back up here, our minimum's minus 27 and our maximum's 21. We just need to write max value equals 21 at x equal to 2, min value equals minus 27 at x equal to minus 2. And we're done there. Higher maths differentiation optimization. What is optimization? It is when you take something and you want to make it like a shape or maximize the size of it or minimize the size of it. So let's say we take an example like this where we've got a length of card 30 centimeters and it has a square side x cut from each corner, so we don't know how big x is, and it makes a box by turning up the sides. Now, show that the volume of the box can be expressed in that as part A. We need to write some algebra for the volume of the box, but getting past that point, find the maximum value of the box. Well, if we've got a expression for the volume of the box in terms of x, maximum value, we're talking about turning points here. Maximum value is a curve when the stationary point equals to 0 and it gives you a maximum turning point. If it asks us to minimize it and we had an equation, then we could say stationary points are equal to 0 and find the minimum turning point. So optimization is just finding stationary points. Let's get straight into it with this example. A square piece of card length 30 has a square cut out x centimeters from each side. An open box is formed by turning up the sides. Show the volume of the box can be expressed as that. So that looks harder than it is. So first of all, just from basic maths, volume of any box is length times breadth times height. So we just need to work out what the breadth and the height of the box is. I've drawn this square around here. If you imagine turning up the sides, you'll have these bits in the corners kind of get cut out. They'll be gone. You have to really think when you're doing these questions. So essentially the base of the box will be the length of the yellow bit, and we need to work out, well, what is the length of that? Well, we have got 30 all the way along, minus x, so it's 30 minus 2x. So I can just write that, 30 minus 2x, and that will be the same for the length because it's a square. So we've got 30 minus 2x times 30 minus 2x. And then, well, how high is the box? Well, if we're turning those bits up, and this length here that I'll highlight is x, then clearly the height of the box is just x. So we can just say times x. Now you can draw a picture to illustrate that if that's struggling to you. If I draw a quick sketch, 30 minus 2x on one side and 30 minus 2x on the other side, and it's x high. So now we can just expand and simplify the volume of our box. So our volume is equal to x is at the end, I'll just put it at the front, times, and then just expand the double brackets, 30 times 30 is 900. We've got 30 times 2 is 60, so that's minus 60 minus another 60 is minus 120x. And we have got 2 2's is 4, so plus 4x squared. And then just check the form we left it in. Yep, we need to expand that again. So that's 900x minus 120x squared plus 4x cubed. We have done it. So that's part A. Now don't worry if you can't do part A, because always in the higher maths exams, you have to do part A, then part B. But if you can't do part A, you can still do part B because they give you the formula anyway. Okay, part B. Find the maximum value of the box. So maximize the volume. You're just thinking when he says find the max, stationary points occur when the differential equals 0. Like that. Max occurs when the derivative, v dash we'll say, or the v by dx equals 0. The v by dx is equal to 900. 2 times 120 is 240, so minus 240x. And 4 3's is 12, so plus 12x squared. So we can rearrange that into the standard quadratic form. So 12x squared minus 240x plus 900 equals 0. And we need to factorize that. But let's hope that 12 is a common factor. And it is. So if I take 12 out, we get 12 times x squared minus 12 into 24 is 2, 20x. And 12 into 90, 24, 12 5's is 60, 72, 84 is 7. 84 makes 60, so it's 5. So 900 divided by 12 is 5. Take your time on that. So that means that we can say we've got x and x, two numbers at times to make 75, but add to make 20. 5 15s is 75, and 5 and 15 make 20. So it's 15 and 5. And it's a minus and a minus. So in this case, x would equal 5 or x would equal 15. Well, what one is it? 5 or 15? We've got some equations for lengths. This length is 30 minus 2x. Well, if x was 15, you would have a length of 0 on the box, so you can't pick that one. That's the same if you end up with a negative. So you pick the one that gives you a positive answer because it's a real world problem. So we can just say x cannot equal 15, so x equals 5. And then we need to check, is it a max or a min? We need to actually justify our answer. So we'll just do a quick nature table. X along 5 along the v by dx or v dash and shape. So just subbing in, I always sub into the factorized form, which is here. Put a number before 5. You can pick any number you want, but I'm just going to pick 1 and 10 and take a little note for myself. 1 minus 5 is negative, 1 minus 15 is also negative, and minus times a minus is a plus, so I know straight away that's positive, so it goes up. It's 0 here, it goes along. Picking 10, 10 minus 5 is 5, that's positive. 10 minus 15, that's negative. A positive times a negative is a negative. So we know that x equals 5 is a maximum turning point. So max value when x equals 5. And if it did ask us, well, what is the max value, which it did say, find the maximum value of a box. Remember, the volume was equal to 900x minus 120x squared plus 4x cubed. So we can just sub that in. So that equals, when x is 5, 900 times 5 minus 125 squares plus 4 times 5 cubed. And you would use a calculator usually to work that out, but that's 4,500. 25 times 120 is 3,000. And 5 cubed is 125. 125 times 4 is 500. So that is 2,000. And the units would be centimetres cubed because it was given to you as centimetres cubed to start with. Let's look at a further example like that. Okay, optimization differentiation example 2. It says an open box with a square base has a volume of 236 centimetres cubed. Taking x as the length of the base, show that the surface area inside the box can be represented as x squared plus 1024 over x, and then find the dimensions of the box that minimise the surface area and calculate its area. So part A is often like the hard part, try to find that formula, but let's see how we get on. So we've got x by x on the box. We don't know anything about its height, so we can just call its height h, but we do know that the volume is equal to 236 centimetres cubed. So let's start off by looking at the surface area. So looking at the surface area of the box, it'll be x times x, which is x squared for the base. So we can write that down. The area is equal to x squared plus, well, we've got 4 of these bits going around the side, so 4 of them. And the dimensions of them are simply x by h, so times xh. So the problem we've now got is, there's no h in the question given, so we need to work out this h, but we do know the volume. Volume is length times breadth times height. Well, length times breadth is x times x, so that's x squared, times the height is h, but we also know that that equals 236. So we can rearrange to make h the subject, and often this will be the case with these questions where you have to use some known information to get rid of that variable h and express it in terms of x. So dividing through by x squared, h is equal to 236 over x squared, and we can just substitute that into our area. So our area is equal to x squared plus 4x times 236 over x squared. Well, hopefully that'll work out, but let's just check. That equals x squared. 4 times 236 is 1024. So plus 1024. And then we've got x over x squared, but we can simplify that by eliminating an x. to get finally our area is x squared plus 1024 over x as required. So we've done part A. Part B says, find the dimensions of the box that minimise the surface area. Minimise or maximise is just differentiation. That's what optimisation is. So even if you can't do part A, part B is worth lots more marks, so don't get worried. We're going to do part B anyway. So for part B, we know our area is above, but we're going to rewrite that in differentiable form. So x squared plus 1024 x to the minus 1. And we want to find the minimise, so we need to find a stationary point. So stationary points occur when we can say a dash or dA by dx is equal to 0. So dA by dx, take 2 down to the front, 2x, take 1 away from the power, so just 2 to the power minus 1. Take the minus 1 down, so minus 1024, and then that's this x to the minus 2. And we're going to make that equal to 0. So we've got an equation to solve. Well, we can't solve an equation with an x minus 2 in it, so let's just make that 2x minus 1024 over x squared equals 0. And then we can just algebraic fraction, we can find the common denominator. So putting that over 1, times them together, we get x squared on the bottom. 2x times x squared is 2x cubed. And then minus 1024 times 1 equals 0. And now, since that equals 0, you can think of this being this equals that times 0, which is 0. So 2x cubed minus 1024 equals 0. So 2x cubed equals 1024, which means that x cubed must equal a half of 1024, which is 512. And when getting a calculator or just working it out yourself, you'll find that the cube root of 512 is 8. So x equals 8 centimetres. Now, there is only one possible solution here, but we still need to check the nature of that. So, using our nature table, we've got x, we're going to go along to 8 and then go along somewhere, dA by dx, and the shape. So we know at 8, we get 0, so it's a long way. We're just checking it as a minimum. So let's just pick a number before 8. We could just pick 1 and 10, say, taking a little note for ourselves. Remember, dA by dx was this thing here, or like this, 2x minus 1024 over x squared. So if I pick 1, I get 2 minus 1024 over 1. 2 minus 1024, that's obviously negative. So we can straight away just say that that is negative when it's 1, so it's going down the way. And then picking 10, 2 tens is 20, minus 1024 over 10 squared. You might need a calculator to work this out. 10 squared is 100, so 1024 divided by 100 is 10.24. 20 minus 10.24, well, that's positive. So we can just save it. It's positive in the shapes here, and therefore x equal 8 is a minimum turning point. And then the question was, find the dimensions of the box that minimise the surface area and calculate the area. So x equals 8 is 1, but we need to write the height because we want the whole dimensions of the box. So we had an expression for the height, remember, way back up here, 236 over x squared. So our height equals 236 over 8 squared, which is 64. 236 divided by 64, just using a calculator, you get 3.6875, so 3.69 centimetres. Now we need to work out the area, but we had a formula for that. We were given it initially. It was x squared, remember, plus 1024 over x. So substituting 8 in, we get 8 squared plus 1024 over 8. That is 64 plus 1024 divided by 8 gives you, using a calculator again, 192. So our area is 192 centimetres squared. And we've answered the question. We've got the dimensions of the box, length and height, and we've got our area. So we're done there. Graph of derived functions for S3 higher maths. So just a little reminder of what happens. If we've got x squared, a quadratic, if we differentiate that, like x squared becomes 2x, well, that's just a linear, a straight line. Any quadratic that you differentiate, you're expecting a straight line. So if we had a picture of a quadratic, which would just be a curve, we would expect a straight line when we differentiate it. Similarly, if you get a cube, you start off with a cubic, well, x cubed differentiates to 3x squared, you're expecting a quadratic when you start with a cubic. Similarly, if you've got a fourth power, you get a cubic, and so on. So here's how you kind of do it. You look to see where it's increasing, decreasing in the turning points. When f of x is increasing, then the derivative is positive, so we draw it above the x-axis. When f of x is decreasing, the derivative is negative, so we draw it below the x-axis. At a turning point, obviously the derivative is 0, so that's a root. It's on the x-axis. Similarly, with a point of inflection is a turning point, so the derivative is 0, so it means it's a root. It's on the x-axis and a turning point. Example 1 says, shown as the graph of f of x, sketch f dash x. So I know that that is a parabola, so I'm expecting a straight line. So all you do is you make yourself a little table, and we're going to go x, and then we're going to go before the turning point, which is -1, and after the turning point. So before -1, the derivative, which is say f dash x, is, we can just check by examining the shape, it's going down the way, negative. At -1, it's a turning point, so it's 0, and after -1, it is rising again, so it's positive. So that means we can examine when we draw this graph, when it's negative, you're going below the x-axis, and when it's positive, you're going above. That's what we need to know. So looking at where it is on the x-axis, it's going to be below, and then it's going to be on it, and then it's going to be above it. So we can then get a little shape. It's very simple. You draw yourself a graph, x and y. We note -1 is where it is on the x-axis, and we just notice it before -1, it is below the x-axis, so it's down here, and above -1, it is above the x-axis. So we're getting a straight line that goes through -1. So there we go, there's the graph of y equals f dash x, and we're done there. Notice on this one, we don't need to do anything with this -11, because we can't say where that is on here. Graphs of derived functions, example 2. Shown as a graph of f of x, sketch f dash x. So again, we draw a little table for ourselves. We've got x, and we're looking at our turning points. So on the x's, it goes to 0 first, and then it goes along. And then the other turning point, it goes along, and then it goes to 3, and then it goes along. So looking at what happens to f dash x, just tracing it. Before 0, it is rising, so it's positive. At 0, it's 0, because it's a turning point, and then between 0 and 3, it's dropping back down again, so it's negative. Still negative here, I suppose. At 3, it's 0, and then after 3, it is rising again, so it's positive. So where is that on the x-axis going to be? So on the x-axis, we're starting above, before 0, then we're dropping to be on it, and then we're going to be below it, staying below it. Once we get to 3, we go on it again, and then after 3, we go above it. So just bearing all that in mind, we can note our points 0 and 3. And we're just saying on the x-axis, before 0, we're above it, so we're starting up here. So I usually just like to draw a little point. And then at 0, we're on the x-axis. And then between 0 and 3, we're below it. So we can kind of just say we're down here somewhere. But after 3, we go back above, which means there must be a turning point down here because I'm dropping, but then I need to turn back round. So we can just draw the graph now. It is clearly a parabola, which goes through 0 and then back up, where that point here would be 1.5, but you don't know how far down it would go. So you get a nice parabola, and then once you've drawn a little sketch, if you feel you want to tidy that up now that you've done it, you can just say, look, I'll make it a nice parabola, 0 and 3, y and x, and this is the graph of y equals f dash x. And we're done there. Graphs of derived functions, example 3, shows the graph of f of x, sketch the graph of f dash x. So again, the same idea, a little table, we're going along to 0 on the x, and then along, and then we're going to go along to 1.5, and then along. So the graph of f dash x, well, before 0, it is rising up, so it's positive. At 0, it's 0. Between 0 and 1.5, we can see it's rising up again, so it's positive again. At 1.5, it's 0. And then after 1.5, we can see we're dropping down, so we're negative. So where is that on the x-axis? Well, we can just write x-axis. We're above, we're on it, we're above it again, we're above it, we're on it, and then we're below. So we need to get our shape, so just draw a nice x and y axis. And again, you would use a ruler, but because I'm working freehand on an iPad here, we'll just ignore the fact that I'm being a bit messy. So just putting our notes in, we've got 0 and 1.5. So I'll just put 1.5 over here in note 0. And then what's happening? Well, before 0, we're above it. So I'll just put a little mark there. Between 0 and 1.5, we're still above it. But then after 1.5, we need to go below the x-axis. So clearly, if we're above it here and we're above it here, crossing this line, it has to go like this before it turns at some point to drop back down. So we can just kind of draw that in. And we get our nice graph there. And if you like, you can remember back from the start, we did say that if you've got a point of inflection, it turns into, on the graph of the derived function, to be a root and the turning point, which is exactly what's happened, but we've just done that by logic. It's went here, it stayed positive and positive, so it's had to drop up and down. But that's just a reminder for you that this turning point becomes a root, and it turns into a turning point as well in the graph of the derived function. Just another quick note on graphs of derived functions. Obviously, if we already know that if you've got f of x is sine x, the derivative is cos x. So if I asked you to draw the graph of the derived function of sine x, you would just draw the cos graph. And similarly, the graph of cos x goes to minus sine x when you do the derivative. So if you did the graph of the derivative of cos x, you would draw minus sine x, which is here. That's the Clown here for Clown Maths. Today we're going to do a bit of a deep dive into the chain rule. Let's jump straight in. Find dy by dx of a derivative of, and we've got y equals 5x plus 1 all cubed. Now, you may be wondering, what is the chain rule? So the chain rule is when you've got some sort of inner function, smaller function, bounded by a bigger function on the outside, in this case, the whole thing cubed. And what you can do when you've got that case is you can think of it like this. Dy by dx is the derivative of the outside function, leaving the inside alone, times the derivative of the inside function. So let's have a look at this example. If I want to do dy by dx of this example, then if we look at our outside function, it's cubed. So we use the power rule, take 3 down to the front, leaving the inside alone, and reduce the power by 1. So it's 3 times the inside squared, and the inside is just 5x plus 1. I now need to do the derivative of the inside function. Well, the inside function is just 5x plus 1, so I need to times by 5, because if you do 5x becomes 5 when you differentiate it, and 1 is just a constant, so that becomes 0. So our final answer, just tidying it up a little bit, is dy by dx equals 3 times 5 is 15, 5x plus 1 squared. So I suppose the main key point to remember is, if you've ever got a function within a function, to find the derivative, you do the derivative of the outside function, just leaving the inside alone, and then you do the derivative of the inside function. Okay. Let's look at a second example where it says y equals bracket x squared plus 3x plus 4 all to the power of 4. So our inside function is just this in pink, and our outside is all that to the power of 4. So the y by dx equals, take the 4 down to the front, leave the inside alone, and reduce the power by 1. So I've done my first differentiation. The inside is just x squared plus 3x plus 4. I now need to differentiate the inside part. So it's going to be times by x squared. You can differentiate using the power rule to 2x. 3x becomes 3 and 4 becomes nothing. So we've got 2 times 2x and 3. We can now just tidy that up a little bit. So dy by dx is simply 4 times my 2x plus 3 times my x squared plus 3x plus 4 cubed. Okay, let's look at some trig. So this one we're going to try and differentiate as y equals sine cubed x. So when it's written like that, it's sometimes best to think of sine cubed x as sine of x cubed, and it's easy to see what's happening. So if I rewrite that as y equals sine x bounded by cubed. You can see your inner function clearly as your sine x and your outer function is to the power of 3. So we differentiate it in the usual way. dy by dx equals 3 to the front, reduce the power by 1, so that becomes 2. Leave the sine x alone. But now I need to differentiate the sine x. Sine, remember, becomes cos, so I'm timesing by cos x. Now we can just tidy that up. So dy by dx is equal to 3 cos x sine squared x, because it's sine of x squared. This is Clear Maths. Today we're going to look at the whole of differentiation in SQA Higher Maths exams, especially for the 2023 exams coming up in May. SQA Higher Maths 2015 Paper 1 question 7 on differentiating a polynomial. A function f is defined on a simple domain by f of x is root x, 3x minus 2 over x root x. Find f dash 4. So we need to get it ready to differentiate. So f of x is equal to root x is x to the half, 3x minus 2 over x times x to the half. So we need to get that all tidied up first. So that is x to the half times 3x minus 2 over x to the 3 halves. And then we can multiply our brackets out to get 3x to the 3 halves minus 2x to the half over x to the 3 halves. And tidying that up even further, f of x is 3x to the 3 halves minus 2x to the minus 1, a half minus 3 halves. Now we can differentiate it, f dash x, take the power down to the front, so it's 3 halves times 3, x to the, take 1 away from the power, so it's a half, minus times a minus is a plus, so plus 2x to the minus 2. Tidying that back up because it was a non-calculator question, so we can substitute 4 in. We get f dash x is equal to 3 3s are 9 over 2 root x, x to the half, plus 2 over x squared. So now we need to substitute 4 in. So f dash 4 is equal to 9 over 2 root 4 plus 2 over 4 squared. That's 9 over 2 times 2 plus 2 over 16. That's just 9 plus an eighth. So we can just write 9 and an eighth if we want as our final answer. SQA Higher Maths 2016 Paper 1 question 2, differentiating a polynomial. So given that y equals 12x cubed plus 8 root x, find dy by dx. So we can, to get it ready to differentiate, 12x squared plus 8 root x is x to the half. So dy by dx, taking the power down to the front, 3 times 12x, take away 1 from the power, squared, plus a half times 8x, take away 1 from the power, minus a half. So dy by dx, 3 times 12 is 36, x squared, a half of 8 is 4, so plus 4x to the minus a half. And there's no reason to make that a positive power because we've just defined dy by dx, so we're done there. SQA Higher Maths 2017 Paper 1 question 8 on differentiating a polynomial. Calculate the rate of change of dt. d of t is equal to 1 over 2t. So we need to get it ready to differentiate. Always need to do that. So d of t is equal to 1 over 2 t to the minus 1. Do not be tempted to move this 2. That's just a half still. Separate it out. It's just the t that's moving. Once we do that, d dash t, take the minus 1 down, so we get minus a half t. Take away 1 from the power, we get minus 2. Then we have to work it out when t is 5. So d slash 5 is equal to minus a half times 5 to the minus 2, or minus 1 over 2 times 5 squared, minus 1 over 2 times 5 squared is 50. So minus a 50th. Just a note, remember, rate of change means differentiate. 2022 Higher Maths, Paper 1, Question 4. Y equals the square root of x cubed minus 2x to the power minus 1, where x is greater than 0. We have to differentiate this expression, so let's get ahead and do that. So our first step, or our first mark, is to rewrite the square root of x cubed is x to the 3 halves. And we've still got minus 2x to the minus 1. If we've written that, we get a mark there for this x to the power 3 halves. We now need to differentiate our terms. So our first mark is for differentiating our first term, which is 3 over 2. X, take away 1 from 3 halves, and that's 1 half. There's a mark there. And then differentiating our second term, minus times a minus is a plus, so it's plus 2x to the power of minus 2, taking away 1. So our final mark is 1 here and 1 for this term here. We do not have to go any further than that in this question. So if you did go further, that's fine, but you don't have to. Higher Maths 2023 Paper 1 Question 1. Y equals x to the 5 thirds minus 10 over x to the 4. So we need to get it ready to differentiate first to find the y by dx. So y equals x to the 5 thirds minus 10 x to the minus 4. And then I can do the y by dx. Take the power to the front. Take away 1, so that is 2 thirds. And then take the power to the front in times, but minus times a minus is a plus, so plus 40 x to the minus 5. You probably don't need to go any further, but just for the sake of completeness, that would give you 5 thirds, x to the 2 thirds, plus 40 over x to the 5, and we're done there. Differentiating a trig function, SQA Higher Maths 2016, Paper 2, Question 11. Show that sin 2x tan x equals 1 minus cos 2x, and then differentiate sin 2x tan x. So part A, sin 2x tan x, well, we can change sin 2x to 2 sin x cos x, and we can change tan x into sin x over cos x. So that gives me 2 sin squared x, and the cos x obviously cancel. So then as an aside, remember we've got a cos 2x on the right hand side. Well, cos 2x, using the expansion with sin squared x in it, is 1 minus 2 sin squared x. So we can rearrange that to get what sin squared x is. That means that 2 sin squared x, moving over to the right, equals 1 minus cos 2x. As required. Part B, f of x is equal to 1 minus cos 2x now. So f dash x, differentiating each function, 1 goes to 0. Cos, remember, goes to minus sine, so it becomes plus sine, so it's sine 2x because of minus minus. And then we need to, because of a chain rule, differentiate the inner function, which is 2, so times by 2. So we get 2 sine 2x. Okay, differentiating a trig function. SQA Higher Maths 2018, Paper 1, Question 3. H of x is 3 cos 2x, find h dash pi over 6. So if h of x is 3 cos 2x, then h, straight away you can just do h dash x is equal to minus sine 2x, well, minus 3 sine 2x, but then we need to times by 2, because we need to differentiate the 2x part as well. So that's minus 6 sine 2x. This is a paper 1 question, so it's an exact value question. So h dash pi over 6 is equal to minus 6 times sine 2 pi over 6. Subbing it in. That equals minus 6 times the sine of pi over 3. Or if you prefer to work in exact values in degrees, that would be 60. So that equals minus 6, the sine of 60, root 3 over 2. 6 divided by 2 is 3, so it's minus 3 root 3. And we're done there. Okay, the chain rule. X squared higher maths 2016, paper 2, question 10. Given it y equals x squared plus 7.5, find the y by the x. And then part B, hence find the integral of this function, which we'll use our answer to part A to do. So part A, the y by the x is equal to, take the half down to the front, x squared plus 7, take 1 off the power, minus a half, and then we differentiate the bit inside the brackets, which is x squared, so that becomes 2x. So that equals 2x divided by 2 is just x, so x bracket x squared plus 7 to the minus a half. And then try to make it look a bit like our part B, that's x over x squared plus 7 to the half, which is equal to x over the square root of x squared plus 7. Part B says integrate 4x over the square root of x squared plus 7, which is very similar. So if I do part B, integrate 4x over the square root of x squared plus 7 dx, well, if I just take that 4 out, I get the integral of x over the square root of x squared plus 7 dx, which I already know is exactly the same as what I found out up here, my differential. This integrated is exactly that, so I can just write the integral as x squared plus 7.5. Simple as that. So that means I've got my answer is 4 times x squared plus 7 to the power of a half. Or, let's make that neater, x squared plus 7 to the half. I've forgot my plus c, so there we are, plus c, and we're done there. Okay, the chain rule. X squared higher maths 2017, paper 1, question 3. Y equals 4x minus 1 to the 12, find the y by the x. Nice and simple, 12 down to the front, 4x minus 1, take away 1 for the power, but then times the bit in the bracket differentiated, in other words, times 4. 4 times 12 is 48, 4x minus 1 to the 11, job done. Okay, the chain rule, S squared higher maths 2019, paper 1, question 6. Given that y equals 1 over 1 minus 3x to the half, and x is not a third, find the y by the x. Let's get it ready to differentiate. So y equals 1 minus 3x to the minus 5. So the y by the x minus 5 in the front, 1 minus 3x, take away 1 from the power, so that's minus 6, and then times by whatever's in the bracket differentiated, which is minus 3. So tidying that up, we get minus 5 times minus 3 is 15, 1 minus 3x to the minus 6, and we're done there. S squared higher maths 2021, paper 1, question 2. Given that f of x is x squared plus 1 to the power 5, find f dash 1. So it's a differentiation question, and it's also the chain rule. So let's find f dash x first. F dash x is equal to, well, I'll take the power down, 5, keep the function the same, x squared plus 1 to the power of 4, but then at times by the inner function differentiated, so I've got x squared plus 1, if I differentiate that I get 2x, so I need to remember to times by 2x, tidying that up, 5 2s are 10, so I get 10x bracket x squared plus 1 to the power of 4. I now need to find f dash 1, so I'm just substituting 1 into this. So f dash of 1 is equal to 10 times 1 times 1 squared plus 1 to the power of 4. 10 times 1 is 10. 1 squared is 1 plus 1 is 2 to the power of 4. That's 10 times 2 2s are 4 times 2 is 8 times 2 is 16. So that's 160. And we're done there. X squared higher maths 2021, paper 2, question 3. Given h of t is the sine of 2t plus pi over 6, determine the rate of change of h when t equals 6. Rate of change means differentiate it. So we need to find h dash t. So this is a trigonometric one, sine. So we check the front of the exam paper and it says that the derivative of sine x is cos x. So we can say that immediately this becomes cos of 2t plus pi over 6. But then the chain rule comes into effect here because we've got this inner function of 2t plus pi over 6. So we differentiate this. Well, differentiate 2t, you get 2. Pi over 6 is just a number, so that's nothing. So the derivative of this whole thing is just 2. We times by the derivative. So there we go, we've got 2 outside as well. And now it says, find the rate of change when t is equal to 10. So we're just substituting 10 into our derivative. So that's 2 times the cos of 2 times 10 is 20 plus pi over 6. So making sure my calculator is in radians, so I don't have to do any conversions because it is a calculator paper. I just press 2 times the cos of, brackets is already open, 20 plus, and I'll open a bracket for pi over 6. So shift pi divided by 6, close the bracket on that, close the bracket on the whole thing, press equals, and we get minus 0.206126 or minus 0.206 ... We can just round that to a reasonable place, so minus 0.2 or minus 0.21 would be fine. I'll just write minus 0.2 to one decimal place, and we're done there. Paper 1, question 12 was, given f of x is 4 sine 3x minus pi over 3, evaluate f dash pi over 6, or f dash, differentiate your function at pi over 6. So, f dash x, we can check the front of the exam paper to realise that sine becomes cos when you differentiate it. So you should first of all start by writing 4 cos 3x minus pi over 3. And just for doing that part without actually finishing the differentiation, which I'm going to do in a moment, gets you your first mark. For your second mark, you have to then realise that this is the chain rule. So you've got an inner function of 3x minus pi over 3. So you need to differentiate that and times the whole thing by that. So in other words, if I differentiate this part, that's the constant, so that's nothing. Differentiate 3x is 3. So I need to times by 3. So we get a second mark for realising that and writing down it. We're going to times by 3. And then our final mark, of course, is evaluating it. So I need to tidy it up and then substitute pi over 6 in. So f dash x equals 12 cos 3x minus pi over 3. So f dash of pi over 6. And this is an exact value, remember, because we are non-calculator. But I'll substitute it in first. 12 cos 3 pi over 6 minus pi over 3. We need to tidy that up. So that's 12 cos 3 pi over 6 minus 2 pi over 6, which is 12 cos 3 minus 2 is 1, so it's just pi over 6. Pi over 6, if you prefer to think in degrees, is 180 divided by 6, which is 30 degrees. So it's the pi cos of 30. If you're not sure of what that is, let's draw an exact value triangle. If this was 60 degrees, that would be 30 degrees up here. This would be 2, this would be 1. 2 squared is 4, minus 1 squared is 1, so that gives you 3. So we get the root 3. And we're looking at the cos, so it's opposite adjacent over hypotenuse, root 3 over 2. So you get 12 times the cos times root 3 over 2. 12 divided by 2 is 6, so you get 6 with the root 3 as your final answer. And for all of that extra work, it's 1 extra mark. A bit stingy of the SQA there. So there's our final mark at this point here. Question 5. A function is defined as f of x is 3 minus 2x to the 4. Calculate the rate of change of f when x equals 4. So again, a power word, the rate of change means differentiation, and then just sub in x equals 4. So f dash x, well, it's the chain rule, so I take 4 down to the front. times by 3 minus 2x, take away 1 to the power, which is 3, but then I need to differentiate then a function, which is minus 2, so I'm timesing the whole thing by minus 2. So f dash x is minus 8, 3 minus 2x cubed, because of the chain rule. Substituting in 4, f dash 4 is minus 8, 3 minus 2 times 4 cubed, that's minus 8, 3 minus 8 cubed, which is minus 8 times minus 5 cubed. Minus 5 cubed is minus 125. 8 times 125. 8 times 125 is 1000. Minus times a minus is a plus. So there we are. Increasing and decreasing functions. SQA Higher Maths 2016, Paper 1, Question 9. Find the x-coordinates of the stationary points on the graph with equation y equals f of x, which is x cubed plus 3x squared minus 24x, and then find the range of values for which a function is strictly increasing. Part A, stationary points, differentiation, make it equal to 0. Okay, so part A, f dash x, 3x squared, 2 3s is 6, so plus 6x minus 24. So stationary points occur when f dash x equals 0. I would always like that statement, and then just make it equal to 0. Taking 3 out as a common factor, we get x squared plus 2x minus 8. So that's 3, double bracket, x and x, 4 and 2, plus 4 minus 2. So that implies that x equals 2 or x equals minus 4. Just the x coordinates, so we're done there. Okay, part B. Determine the range of values for which the function is strictly increasing. So we need to work out when it's increasing, so we're going to do a nature table and work out that. So part B, using our nature table, we're going to go along in the vicinity of minus 4, and then we're going to go along, and then we're going to do the same to 2, and then along. Notice I split this up into 2 turning points, just in case the function is not continuous here. That just saves me any bother. Okay, so that's my x. So my f dash x at this point, well, we already know that it's 0 at these 2 places. So pick a number before minus 4, it's minus 5. And it's always easy to substitute into the factorised form to work this out, but you can just do this in your head or do the work on a bit of paper. I'll do it in my head. So we've got minus 5 minus 2, which is negative, minus 5 plus 4, which is negative. A negative times a negative is a plus, so that's positive. After minus 4, let's just pick any number, pick 0. Minus 2 is 0, that's negative, that's positive. Negative times a positive is a negative. So we already know this one's going to be negative because it's the same idea before 2. After 2, 3 minus 2 is 1, 3 plus 4 is 7. Positive times a positive is a positive. So our shape is going up the way, then along the way, then down the way, and for this side it's going down the way, along the way, then up the way. And we'll have to work out when it's strictly increasing. So it's increasing when x is less than minus 4 or x is greater than 2. Increasing and decreasing functions, SQA Higher Maths 2018, Paper 1, Question 15. This is a cubic function set of real numbers, and we're given a bunch of information. X plus 4 is a factor. That means that x equals minus 4 is a root. X equals 2 is a repeated root. Well, repeated root, remember, means the turning point is also at that point. So we also have a turning point at x equal to 2 on the x-axis then. F dash minus 2 equals 0 also implies a turning point at x equal to minus 2, but that could be anywhere, so it could be under or below. But then we also know that when it crosses the y-axis, the gradient of the tangent is greater than 0, so it's going up the way after it crosses the y-axis. So we can now start to draw a possible diagram, and this is just one possible answer, but as long as it's consistent with all the information, we'll be fine. So let's put in our -4 root. Let's go there. Our -2 where it's a turning point, and our 2 over here, which is a repeated root. So drawing it in red to be clear. Since it's rising at this point where it cuts the y-axis, then, and this is a turning point, it must drop down here, turn at -2, rise back up, turn at 2 again, and then drop back down, because we also know that 2 is a turning point. So there you go, we have managed to do that. We're showing that -2 is one of the turning points. We've got x equal to 2 here and -4, so we've got a possible graph, and we're done there. Increasing and decreasing functions, SQA Higher Maths 2018, Paper 2, Question 3. A function is defined as a set of real numbers given by f of x is x cubed minus 7x minus 6. Determine whether f is increasing or decreasing when x equals to 2. So we need to work out the gradient of the tangent at x equal to 2. So f dash x is equal to 3x squared minus 7. At x equal to 2, f dash of 2 in other words, we get 3 times 2 squared minus 7. That's 3 times 4 is 12, take away 7 equals 5. And then we need to write a little statement. Since f dash of 2 is greater than 0, the function is increasing at x equal to 2. And we're done there. Increasing and decreasing functions, SQA Higher Maths 2019, Paper 2, Question 7. Express this in the form p x plus q squared plus r. Now let's complete the square. So for part A, if we look at these two, we can take -6 out as a common factor. So we get -6, and we get x squared minus 4x. 6 times 4 is plus 24. Take away 25, sitting on the end, and then we just completely square the normal way on this term. So we've got, that gives you -6, half the middle term, x minus 2, all squared, and then immediately take away 2 squared, and we've still got minus 25 on the end. Just be aware that this is all times by -6 though, so we need big brackets around it. So that gives us -6, x minus 2 squared. 2 2's is 4, 4 6's is 24. So we get plus 24 minus 25 sitting on the end. So that's -6, x minus 2 squared. 24 minus 25 is -1. Part B says, given that f of x is minus 2x cubed plus 12x squared minus 25x plus 9, show that it's strictly decreasing. So to show that something's increased or decreased, we need to evaluate the gradient of the tangent, and let's differentiate. So let's look at f dash x. F dash x equals 3 times 2 is 6, so minus 6x squared. 12 times 2 is 24, so plus 24x, and minus 25. So we've differentiated it, but notice that is minus 6x squared plus 24x minus 25 is exactly what we were asked to do with something with completing the square on part A. So it's to do with the fact that it's completed the square. So we can now just say that f dash x now equals minus 6x minus 2 squared minus 1. If I pick any number for x here and I square it, I get a positive number. So that means I can then say x minus 2 squared is positive for all values of x. And that means that when I've got a positive times a negative is a negative. Take away another one, gives me a negative as well. So all I need to then say is, therefore, minus 6x minus 2 squared minus 1 is negative for all values of x. So f of x is strictly decreasing. And we're done there. Values for which the function f of it, SQA, Higher Maths 2023, paper 2, question 10. Determine the range of values for which the function f of x is 2x cubed plus 9x squared minus 24x plus 6 is strictly decreasing. There's actually two ways to do this. Both involve stationary points. If you get the stationary points, you can then examine the graph to see where the derivative is negative, or you can just examine the nature of the stationary points. So let's just look at the stationary points first. Stationary points occur when f dash x is 0. So f dash x gives me 6 2's is f dash x, 3 2's is 6, 6x squared, 2 9's is 18, plus 9 18x, and minus 24. And I'm going to look at that equal to 0 for our stationary points. 6 is a common factor, so I get x squared plus 3x minus 4 goes 0, so double bracket that up. X and x. 4 and 1 make 3, plus 4 minus 1 makes 3, so that implies our stationary points occur when x equals 1 or x equals minus 4. So then there's two ways to go now. I'll give you both options. I'll use the nature table. If you're using a nature table, you'll go along to minus 4, along, and then along to 1, and then along. And then you're just going to examine the derivative. So looking at our derivative, a number before minus 4, let's try minus 5. Minus 5 minus 1 is minus 6. And minus 5 plus 4 is minus 1. A minus times a minus is a plus. So it's positive there. It's 0 here. Between these two numbers, let's just try 0 then. Minus 1 times 4 is minus. It's negative there, so it's still negative there. It's 0 there. And then a positive number like 2. 2 minus 1 is 1. 2 plus 4 is 6. Positive times a positive is a positive. So it's increasing before minus 4. And then it's a turning point. And then it's decreasing. Still decreasing, of course. And then it's increasing. So we could say strictly decreasing when minus 4 is less than x is less than 1 in between those two numbers. Or if you, and that works as well because the function is continuous. If it was discontinuous, you'd be a little bit knackered, but we know it's continuous because it is. Now, if we move on to the other way, we could look at just the graph. So graph of the derivative, we know the derivative is quadratic with stationary points at minus 1 and 4. So 1 and 4, so 1 and minus 4, sorry. So 1 and minus 4, and it's a normal there. So same idea. That's the graph of the derivative. That's the graph of f dash x. And that's negative below the x-axis, which is down here. So it's between minus 1 and 4. So again, you would stay the same answer. Minus 4 is less than x is less than 1. Either of those options will give you your marks probably. Equation of a tangent to a curve. SQA Higher Maths 2015, paper 1, question 2. Find the equation of a tangent to the curve y equals 2x cubed plus 3 at a point x equals minus 2. Equation of a tangent means differentiate and sub in the number. So step 1, dy by dx. 3 times 2 is 6x squared. So at x equal to minus 2, dy by dx equals 6 times minus 2 squared. 6 times 4, which equals 24. So dy by dx is 24, which remember is equal to our gradient m. When x is minus 2, y equals 2 times minus 2 cubed plus 3. That's 2 times minus 8, add 3. Minus 16 plus 3 is minus 13. So our point is minus 2 minus 13, and our gradient is 24. So that means that y plus 13 equals 24 x plus 2. Y plus 13 is 24x plus 48, or y equals 24x plus 48 minus 13 is 35. And we're done there. SQA Higher Maths 2015 Paper 1 Question 11 for the equation of a tangent to a curve. Question 11 says the point t minus 2 minus 5 lies in the circumference of the circle with this equation. Find the equation of the tangent to the circle through t. For part A, so the part A is a circle question, and part B says the tangent is also a tangent to a parabola. With that equation, determine the value of p. So let's do part A, circles. The centre of our circle is just minus 8, minus 2. Minus 8 and minus 2. And we've also got our point T, which is minus 2, minus 5. So if we work out our gradient, if we draw a circle for this, there's our C, there's our T, say, out here. That meets the tangent at right angles. So the gradient between C and T is perpendicular to the tangent. So the gradient of CT is equal to minus 5 minus minus 2 over minus 2 minus minus 8. Minus 5 add 2 is minus 3. Minus 2 add 8 is 6. That's equal to minus a half. Therefore, the gradient of the tangent is 2, since m1 times m2 equals minus 1. And then our point, remember, is minus 2 minus 5, so y minus minus 5 equals 2x minus minus 2. So y plus 5 equals 2x plus 4, or y equals 2x minus 1. And we've got the equation of our tangent. Part B says the tangent is also a tangent to a parabola of equation y equals minus 2x squared plus px plus 1 minus p, where p is bigger than 3. Find the value of p. Well, if it's a tangent to that parabola, it means that y equals 2x minus 1 goes into this, so we can just equate them in simultaneous equations. So we can just say that 2x minus 1 equals minus 2x squared plus px plus 1 minus p, and solve that equation to get our x. So moving everything over to the left, we get 2x squared because it's negative. We've got plus 2x, then minus px, and then we've got minus 1, minus another 1, but then plus p, and that would equal 0. Equating all our terms, so we get an x squared, x and a number. You get 2x squared. We can factorise x out here, so we've just got x, so it's 2 minus p times x. And then we've got minus 2 plus p equals 0. So we've got a quadratic, but when you get a quadratic, it only has one solution, or it only touches at one point when the discriminant equals 0. So tangent, therefore b squared minus 4ac equals 0. So our b is 2 minus p, so 2 minus p squared minus 4 times a times c, which is minus 2 add p, equals 0. Multiplying that out, 2 2s is 4, minus 2 times p is 2p, so minus 4p plus p squared. And then you've got 4 times 2 is 8, so it's minus 8 times minus 2 plus p. So you get 4 minus 4p plus p squared plus 16 minus 8p equals 0. So p squared, and then our p terms, we've got a minus 8 minus 4 is minus 12p, and then our constant terms, 16 plus 4 is 20, equals 0. So we've got a quadratic to solve it. We can now factorise, hopefully. If that equals 0, then we get p, and p, 10 and 2 to make 12 in the middle, and it'll be minus 10 and minus 2. So p equals 2 or p equals 10. But if you go back to the original question, it says p is greater than 3, so we can disregard that one. So p equals 10 as our final answer. SQA Higher Maths 2018, Paper 1, Question 7 for the equation of a tangent. You've got this curve shown in the diagram. Write down the coordinates of p, the point where the curve crosses the y-axis. So for part A, cuts the y-axis when x equals 0. So subbing 0 in, that's really easy. 0 minus 0 plus 0 plus 5. When x is 0, y is 5, so it's 0, 5. Part B, determine the equation of a tangent to the curve at P. The equation of a tangent, I can find the gradient by differentiation. So dy by dx is equal to 3x squared minus 6x plus 2. And at the point P, P already we know is x equal to 0, y equals 5. So when x equals 0, dy by dx equals 3 times 0 squared minus 6 times 0 plus 2. 0, 0 plus 2 equals 2. So our gradient equals 2, and our point P, remember, is equal to 0, 5. So y equals mx plus c is the easiest one to use here. Y equals 2x plus 5. Or you could use y minus b equals mx minus a and still get 2x plus 5. Question C. Find the coordinates of Q, the point where the tangent meets the curve again. So you're just going to solve simultaneous equations here. X cubed minus 3x squared plus 2x plus 5 was our curve. It's equaling 2x plus 5 at points of intersection. So we can solve that quite easily. If these cancel each other out, if we take it over, minus 2x minus 5, they disappear. So that just leaves me with x cubed minus 3x squared equals 0. Common factor of x squared, so you get x minus 3. So that means that x squared equals 0, so x equals 0, or x minus 3 is 0, so x equals 3. Well, we already know 0 is one of our points, so the second point of intersection is that x equal to 3. So when x equals 3, y equals 2x plus 5. So that is 2 times 3 is 6 plus 5, which is 11. The second point is 3, 11, and we're done there. SQA Higher Maths 2021, Paper 2, Question 1 on differentiation. Determine the equation of the tangent to the curve y equals 2x cubed minus 8x squared plus 14 at the point x equals 3. So equation of the tangent means we can do differentiation to get the gradient of the tangent. So let's start off by doing that. So our gradient is simply dy by dx. Well, that is 3 2s are 6x squared, 2 8s are 16, so 16x. And that's at the point x equals 3, so at x equal to 3, our gradient is equal to 6 times 3 squared minus 16 times 3. Use a calculator anytime you want. 3 3s are 9 times 6 is 54. 3 times 16 is 48. 54 minus 48 is 6. So we know our gradient is 6. And remember from straight line, to find the equation of a straight line, which is what a tangent is, we need a point and the gradient. So we've already got the gradient. We've got a bit of a point. It says x equals 3. So we can work out our y just by subbing 3 in. So when x equals 3, y equals, it's 2 times x cubed, 2 3 cubes, minus 8 times 3 squares plus 14. 3 3s are 9 times 3 is 27. If you double 27, you get 54. 3 3s are 9, 9 8s is 72, so minus 72 plus 14. Anyway, you can get a calculator anytime you want to work any of this out, but you get minus 4. So our gradient, remember, is equal to 6, and our point is 3 minus 4. So that's my a and b for y minus b equals mx minus a. Y minus b equals mx minus a. Y minus minus 4 equals 6x minus 3. So y plus 4 equals 6x minus 18. Or y equals 6x minus 18 minus 4 is minus 22. And there we go, equation of a tangent. Higher Maths 2023, Paper 2, Question 2. Find the equation of the tangent with... Find the SQA Higher Maths 2023, Paper 2, Question 2. Find the equation of the tangent to the curve with equation y equals 2x to the 5 minus 3x at the point x equals 1. Equation of the tangent, therefore, we need the gradient using dy by dx, and then y minus b equals mx minus a. So our gradient, first of all, our gradient equals dy by dx, remember. That is 5 times 2 is 10, x to the 4, taking away 1 to the power, and minus 3. So at x equal to 1, our gradient equals 10 times 1 to the power of 4 minus 3. 1 to the power of 4 is just 1, so that's just 10 minus 3, which is 7. Now we need a point. So when x equals 1, y equals, I substitute it in, 2 times 1 to the 5 minus 3 times 1. Remember, using a calculator anytime you want, but that's 2, take away 3, which is minus 1. So our point is 1 minus 1, and our gradient is 7. So we can use y minus b, y minus minus 1 equals 7, x minus a, which is 1. So y plus 1 is 7x minus 7. So y must be 7x minus 8. And we're done there. Stationary points under nature. SQA Higher Maths 2016, Paper 1, Question 9. Find the x-coordinates of the stationary points in the graph with this equation, and then determine the range of values with which the function is increasing. So part A, stationary points occur when f dash x equals 0. So f dash x is equal to 3x squared plus 6x minus 24. So setting that equal to 0. 3 is a common factor, so we get x squared plus 2x minus 8. And we can double bracket that hopefully up quite easily. X and x, 4 and 2, plus 4 minus 2 equals 0. So that means that x equals 2 or x equals minus 4. The 3 doesn't matter because it's just times them by 0. Part B, hence find the range of values for which values of x for which a function is strictly increasing. So we're going to use a nature table for that. So for part B, looking at our stationary points, it goes along and then hits minus 4 and then it goes along. So there's our first turning point and our second turning point along to 2 and then along. So that's x, and then looking at f dash x. So we can just sub into this one in our heads really. So we know it's 0 here and here. So picking a number before minus 4, let's say minus 5, that'll be negative. Minus 5 take away 2. Minus 5 add 4 is also negative. A negative times a negative is a positive. A number after minus 4, let's just pick 0. You get a negative times a positive. That's a negative. So it'll be the same on this side. And after 2, 3 minus 2 is 1. 3 add 4 is 7. They're both positive. Positive times a positive is a positive. So looking at our shape, we have got along, or then along, then down, or and then the second turning point, down, along, and then up. So the range of values for which the graph is increasing is just this one here and this one here. So it happens when x is less than minus 4 or when x is greater than 2. And we're done. Okay, stationary points under nature, SQA Higher Maths 2017, Paper 2, Question 7. Find the x-coordinate of the stationary point on the curve with equation y equals 6x minus 2 root x cubed. Then find the greatest and least values of y in interval 1 is less than or equal to x and less than or equal to 9. So part A, stationary points occur when the y by dx is 0. So we need to get it ready to differentiate. So with part A, I've got y equals 6x minus 2. I've got x cubed, so the cubed comes along for a ride, but it's a square root, so it's over 2. The y by dx then, 6 minus 2 times 3 over 2, x to the half, because I take away 1 from the power, and then we can say that stationary points occur when the y by dx equals 0. So making this equal to 0, we get 6. These 2's cancel, so minus 3. X to the half equals 0. So 3x to the half equals 6. X to the half equals 2. Remember, x to the half means the square root of x equals 2. So I'm looking for, if I square both sides, I get x equals 4. And we're done there. Part B, hence determine the greatest and least values of y. So at x equal to 1, y equals 6 times 1 minus 2 times the square root of 1 cubed. 6 times 1 is 6, minus 2 equals 4. At x equal to 9, the other one, y equals 6 times 9, minus 2 times the square root of 9 cubed. 6 times 9 is 54, minus the square root of 9 is 3, so 2 times 3 cubed. 54, 3 3s are 9 times 3 is 27, 27 times 2 is 54, that gives me a big 0 is the answer at the limits. So now I need to evaluate it at x equal to 4. So at x equal to 4, we've got y equals 6 times 4, minus 2 times the square root of 4 cubed. 24 minus 2 times the square root of 4 is 2, so 2 cubed. 24, 2 cubed is 8 times 2 is 16. 24 minus 16 is 8. So then we can just state our greatest and least values. The greatest value is 8 and the least value is clearly 0. So greatest value equals 8, least value equals 0. And we're done there. Stationary points in our Nature History Higher Maths 2019 Paper 1 Question 1. Find the x-coordinates of the stationary points on the curve with equation y equals a half x to the 4 minus 2x cubed plus 6. Stationary points occur when the y by dx equals 0. So we can find the y by dx. 4 times a half, well that's 2x cubed, take away 1 from the power. 3 times 2 is 6, so minus 6x squared, and then 6 goes to nothing. In our little statement, stationary points occur when the y by dx equals 0. We've got 2x cubed minus 6x squared equals 0. Common factor of 2x squared to get x minus 3. And that means that x equals 0 because 2x squared equals 0, or x equals 3. And there we are. Simple as that. SQA Higher Maths 2021, Paper 2, Question 6. The graph of the function f of x equals 6x minus 2x to the power of 3 halves is shown for x greater than or equal to 0. The point A is a stationary point of f of x, and it also shows us the roots at 0 and 9. Determine the x-coordinate of the stationary point. Stationary points occur when the derivative equals 0. So for part A, stationary points occur when f dash x equals 0. So we work out f dash x. So looking at our original function, we've got 6x becomes just 6. Minus, we've got 3 halves times 2. 2 3s are 6, divided by 2 is 3, so minus 3x. And then taking away 1 from the power, 3 halves just become a half. And we're going to need to make that equal to 0. So making that equal to 0, we've got a little equation to solve. So I'll do 6 minus 3 root x equals 0. 3 root x, the subject, equals 6. Moving it over to the right. So the square root of x equals 2, 6 divided by 3. If the square root of x is 2, by squaring both sides, x must equal 4. And that's the x-coordinate of the stationary point. Doesn't ask for the y, so we'll just move on and say hence calculate the shaded area. So part B is really an integration question, so because for area is integration. Part B is the integral between, well, we're on the x-axis, we've got the shaded region, so we're starting here at the turning point and we're going to 9. Well, we know the turning point was 4, so it's between 4 and 9 of the original function, 6x minus 2x to the 3 halves. I'll write dx. So integrate is the opposite of differentiation. You add 1 to the power and divide by the new power. So that's a little 1 on there. So adding 1 becomes x squared. 6 divided by 2 is 3. 3x squared. And then adding 1 to 3 halves becomes 5 halves. So I need to do 2 divided by 5 halves. And that's going to be between 4 and 9, what we're going to substitute in a minute. So let's just tidy this up a little bit. That's 3x squared. Now, if you divide by a fraction, it's the same as times it by its reciprocal. In other words, 2 times 2 over 5. 2 2s is 4 over 5. So it's minus 4/5 of x to the 5 halves. And that's between 4 and 9. So we're going to substitute 9 in and 4 in, and we can use a calculator for any time we want. So substituting 9 in, we get 3 times 9 squared minus 4/5 of 9 to the 5 halves. And that's going to be taken away. What happens when you substitute 4 in? 3 times 4 squared minus 4/5 times 4 to the 5 halves. Now, if you can get this far, you've already got most of the marks. It's usually only one extra mark for working all this out. So if it's going to take you too long or you make a mistake, don't worry too much about it. But let's go on and actually work this out. We've got 3 times 9 squared minus 4/5. Calculator's getting a workout on this one. Times 9 to the power of, and it's 5 halves. That gives me 243 over 5. And if you've got a nice calculator, it'll give you it as a fraction. So there's 243 over 5 for my first bit. And then my next bit, 3 times 4 squared minus 4/5 of, and it's 4 to the power of 5 halves. That's 112 over 5. So it's minus 112 over 5. Since I've got my calculator, I might just work that out. 243 minus 112 is 131. So that gives me 131 over 5 square units, because there's no units in the question, but it is an area, so I like square units. And we're done there. XQA Higher Maths 2023 Paper 1 Question 8. A function is defined a set of real numbers by x cubed plus 3x squared minus 9x plus 5. Find the coordinates of the stationary points of f and determine their nature. Stationary points means derivative equal to 0. So we can write stationary points occur when f dash x equals 0. So f dash x is equal to 3x squared. 2 times 3 is 6, so 6x minus 9, and then the 5 disappears. So we're saying 3x squared plus 6x minus 9 equals 0. 3 is a common factor, so we get x squared plus 2x minus 3 equals 0. It's keeping our common factor, a standard one to factorise. We've got x and x. It has to be 3 and 1. And plus 3 minus 1 is 2. So that implies x minus 1 is 0, so x equals 1. Or x plus 3 is 0, so x equals minus 3. So we've now got our x part of the coordinate. We might as well try and find our y part. So when x equals 1, y equals, substitute into the original, x cubed plus 3x squared minus 9x plus 5. 1 cubed plus 3 times 1 squared minus 9 times 1 plus 5. So that gives me y equals 1 plus 3 minus 9 plus 5. Y equals 1 plus 3 is 4. 4 plus 5 is 9. Minus 9 is 0. So our first coordinate is 1, 0. When x equals minus 3, we can do the same thing. So y would be minus 3 cubed plus 3 times minus 3 squared minus 9 times minus 3 plus 5. So keeping your wits about you, because it is an on calculator. 3 cubed is 27, so you get minus 27. 3 squared is 9 times 3 is plus 27. 9 times 3 is 27, but it's plus because of a minus times a minus. And then you've got plus 5. Minus 27 plus 27 is obviously 0. So then you've got 27 plus 5, 32. So your second stationary point is minus 332. So there's my two stationary points. Now we need to determine their nature by using a nature table. So a nature table is like this. We're going to go along to our first point. This is our x, so minus 3. and then along. And then we're going to examine the other stationary point. So I'm going to go along to 1, and then along. I always keep it separate in case there's a point of a discontinuous point. I don't want to lose marks for it in this case, but just in case. So then we're just looking at our derivative, f dash x. So picking numbers, we know that at -3 it's 0, and at 1 it is 0. So we need a number less than -3. Now, it's always best just to read a derivative to examine it already factorised. So just pick a number less than -3. Let's just pick -4. -4 minus 1 is negative. -4 plus 3 is negative. A negative times a negative is a positive. So I know it's positive before -3. So I can just write that. And after -3 but before 1, let's just put 0 in. That gives you negative, and that gives you positive. Negative times a positive is a negative. So we know that it's negative here. And therefore, after -3 but before 1, it's still negative. After 1 though, just pick 2. 2 minus 1 is positive. 2 plus 3 is positive. Positive times a positive is a positive. So we get a positive again. So our shape, it goes up, along, and down. So max, down, along, and up. So it's a min. So we need to state that. So -332 is a maximum turning point. And 1, 0 was it? 1, 0 is a minimum turning point. And we're done. Graph of the derived function. SQA Higher Maths 2019, paper 2, question 5. The diagram below shows the graph of a cubic with stationary points at -2 and 4 as shown on the diagram of your answer book. Sketch the graph of g dash x, the derivative. Okay, so let's just draw a picture here. Y and x. Now, we should first of all look at this. It's telling us it's a cubic. A cubic differentiates to a quadratic. So we're expecting a quadratic either going down the way or up the way. And we really just need to identify the roots. Well, the roots happen when the turning points, because the derivative equals 0. So it's just, I need to know that stationary points occur when dy by dx is 0, which means that these are my roots. So I get a root at -2 and a root up at 4. So that means that if we examine before -2, it's going up the way, it's then dropping down the way, and the derivative will be going back up the way. So it's above the x-axis before -2, it's below in between the roots, and it's above again after 4. So that's how I like to think of this. So I know I'm starting high, I'm dropping below between the numbers, and then I'm going high again. So my curve must come down like so. Obviously, I can't quite get the turning point. I know the turning point happens at 1 in the middle of the roots, but I don't know exactly what it would be on the y-axis, so I don't need to work that out. And there we are. There's my graph of the derivative. SQA Higher Maths 2021, paper 2, question 7. The diagram shows the graph of the y equals f of x, which has stationary points at -1 and 3, shown in the diagram. We have to draw on the diagram in your answer book a possible graph of the derivative, f dash x. So it's a graph of the derivative. So remember how this works. We draw a little table for ourselves, and we examine going along to the turning points. We're at -1, and we're going along to 3. And we can say the derivative f dash x, and then we can say what's happening on the x-axis, because we want to go above or below. So just tracing this, before -1 it's negative, at -1 it's 0 of course, after -1, but between 3 it's positive, at 3 it's 0, and after 3 it's positive again. So in terms of where we are on the x-axis, we're below to start with, and then we're on, then we're above, and then we're back on, but then we stay above. So this is what you call a point of inflection. When that happens, this point ends up being a turning point on a derivative, but also a root. But you'll be able to see that straight away when you draw your graph. So I'm going to draw a quick sketch. Where's a y-axis? And there's an x-axis. Noting our main points, which are -1 and 3. So let's call -1 there. And let's say that 3 is way over here. And taking little notes for ourselves. Before -1 we're negative, which is below. So I'll just put a wee point for myself. At -1 we're on. Between -1 and 3 we're positive. So we're up here. But after 3 we're still positive. Whereas at 3 we're on. So it has to go up through here, turn around and go down. So kind of tracing it with a laser. It has to kind of go like this and then go back down and then flip it back up. So we just kind of draw that diagram as best we can. Something like that would be a reasonable graph. The graph of y equals f dash x. And we're done there. Paper 2015, paper 2, question 8 of SQA Higher Maths. This is a crocodile stock in play located 20 metres further upstream on the opposite side of a bank. Crocodiles travel at different speeds on land and water. The time taken for a crocodile to reach this place is minimised if it swims to a particular point p metres upstream on the other side of the river as shown. And then it gives you a formula for the time taken in tenths of a second given by this. Remember, x is this horizontal distance here. Part A says calculate the time taken if the crocodile does not travel on land. It was the context of the question, I think, that made this one difficult and people couldn't quite understand what's it asking me here. Well, if it's asking me basically this, if it doesn't travel on land, it is in the water. If it's in the water, it's just swimming straight upstream at 20 metres. So part 1 actually is just substituting x equals 20 into this formula. So part 1, t of 20 is 5 root 36 plus 20 squared plus 4 times 20 minus 20. Well, that's 0. So that's just 5 plus the square root of 36 plus 400. And that equals 5 times the square root of 436. And that is 100. And once you get your calculator out, you do square root of 436, times it by 5, and you get 104. And just remember your units, it's tenths of a second. So that's part 1 done. Now let's look at part 2. Calculate the time taken if a crocodile swims the shortest distance possible. Well, let's have a look at this picture again. Swims the shortest distance. Well, a straight line is going to be the shortest distance. So if he just jumps straight up here and then walks the rest of the way, he must be walking 20 metres. So that means that he spends no time in the water. Because remember, x is how far he swam basically upstream. So he's not swum anything upstream, he just went straight across and he's went 20 metres on land. So in other words, x is 0. So for part 2, you just have to substitute t equals 0 in to the formula. So you get 5 times the root of 36 plus 0 squared plus 44, times 20 minus 0. 5 times 6 is 30, 4 20s is 80. That gives us 110 tenths of a second. Part B, although the context of the question was quite unusual, to say the least, between these two extremes there's one value which minimises the time taken. If you're a higher maths pupil, you should realise that the word minimise means we're doing optimisation. And that should be a big key red flag for you. Find this value of x and hence the minimum possible time. So step 1, I need to get it ready to differentiate. So if we look at our t of x, we can do the surds can come a power. So that's 36 plus x squared to the power of a half plus 80 minus 4x just by multiplying out the bracket. Now we can differentiate this using the chain rule for this part. T dash x is equal to 5 times a half, taking the power down, 36 plus x squared to the minus a half. And then we need to differentiate the 36 plus x squared because of the chain rule, so times 2x. and then we'll still have take away 4 on the end because that's 0 and that is differentiates to 4. Tidying that up, we get 5 over 2 times 2x, 36 plus x squared to the minus a half, take away 4. 5 times 2 is 10, divided by 2 is 5, so you've just got 5x for the first term. We could say that's over 36 plus x squared to the half minus 4, or that's 5x over the square root of 36 plus x squared, take away 4. Now we need to look at our stationary points because we're trying to minimise the time taken, so it's an optimisation question. So just remember, for stationary points occur when t dash x equals 0. So we've got our equation 5x over the square root of 36 plus x squared minus 4 equals 0. Okay, moving the 4 to the other side, we get 5x over the square root of 36 plus x squared equals 4. And then we can multiply through by the denominator. In other words, 5x equals 4 times the square root of 36 plus x squared. And we can square both sides to get 25x squared equals 16 times 36 plus x squared, because opposite of a square root is squaring. And we can work that out. 25x squared equals 576 plus 16x squared. Moving the x squared over to the other side, taking away 16, you get 9x squared is 576. So x squared is divided by 9, 64. So x equals 8 or x equals minus 8. But straight away, minus 8 is not valid because x has to be a positive number. X is greater than 0 or equal to. So x equals 8 is our number. So the minimum time taken occurs when x equals 8. There's no need for a nature table this one because we know it's going to be a minimum. So minimum time when x equals 8. So we can then substitute that back into our t of x. So remember that would give us t of 8 equals 5 times the square root of 36 plus 8 squared plus 4 times 20 minus 8. And if you were to work that out using a calculator, you would get 98 tenths of a second. Optimisation SQA Higher Maths 2016, Paper 2, Question 7. It says, a council setting aside an area of land to create 6 fence plots. Each plot has a rectangle measuring x by y, and it says the area of land being set aside is 108. Show that the length of fencing is given by this. So let's start working on the length first of all. And then we'll probably have to use the area to change our y to an x because this thing's only got x's in it. So our total length. So let's just count. We've got 1, 2, 3, 4, 5, 6, 7, 8y plus 1, 2, 3, 4, 5, 6, 7, 8, 9x. So 9x plus 8y or 8y plus 9x. But our length has got only x's in it, so I'm going to have to use my area. So if I look at the area, well, if I notice this is y and this is x and x, I've got 2y on the height and times 3x, length times breadth, on the bottom. So 2y times 3x is equal to 108. So that means that 6xy equals 108. So I can replace this y by dividing by 6x. Y is 108 divided by 6x. So I can do 108 divided by 6x. So that simplifies to 18 over x. So now for our length, L of x, which was 8y plus 9x, we can replace the 8 and the y by 18 over x plus 9x. And we're trying to make it look like 144 over x. Well, let's hope. 8 times 18. 8 8s is 64. 8 1s is 8. 8 plus 6 is 4. That's 14. So our length of x is equal to 144 over x plus 9x. Or to make it look exactly the same as we're given in the question, 9x plus 144 over x. And we're done there. Part B, L of x is equal to 9x plus 144 x to the minus 1, taking the x up. So L dash x is equal to 9 minus 144 x to the minus 2. Or we could say 9 minus 144 over x squared. Now, for minimization, we need to find stationary points. So stationary points occur when the derivative equals 0. So 9 minus 144 over x squared equals 0. And then we need to solve that equation. So timesing everything through by x squared, since we've got an algebraic fraction. Or we'll start by saying 9 is 144 over x squared, because that makes it simpler. So that implies that 9x squared equals 144. So x squared is 144 divided by 9. Let's just do that quickly at the side. We get 1596, 16. So x is the square root of 16. Which is equal to 4 because, and it's actually equal to minus 4 as well, or minus 4, but we'll just disregard it because x cannot be negative because it actually has a real length we're looking at. So we're just looking at that turning point of 4. So that's why you need to watch. When you do your turning points, if it's a real life question, you get a negative answer sometimes, you just disregard it. So looking at our table of signs, we've got x, we're going along to 4 and along, and then L dash x. Well, in the vicinity of 4, remember L dash x is equal to 9 minus 144 over x squared. So apart from 0, you can't pick 0. 3 3s is 9. 9 into 144 is 16. That's negative. 9 minus 16 is negative. So we get a negative. We get 0. And picking any number after 144, it should be clear that 9 minus a small number, because it's going to be a fraction, is going to be positive. So that means our shape is down, along, and up. And therefore, minimum at x equal to 4. And we're done there. Just a note on the table of signs. So if you'd use minus 4, you could have done along minus 4 along, but then you'd have to go along 4 along, and you'd have to still disregard that minus 4 because it can't be minus 4. So you're better off just disregarding it up here. But notice I don't pick numbers here, because if you try and pick 0, you're done. So I will always just draw an arrow to show that it's in the vicinity of 4. Question carefully, it's really just an optimization question. Have a look, see if you can have a go at it, and then come back when you're done. Minimize the cost of production. Minimize optimization. That's your key power word for higher maths there. Let's try part A in any case. So there is our box and all the information in it, and I want the surface area. So I'm just going to start working on it and see if I can get the answer close to what we have got. So surface area, we've got 3x times h, and I can see I've got 1 of them, 2, 3, 4 of them. So first of all, I can write down, I've got 4 times 3x h. I'll put a dot for times in so it's clear. And then I need to add on, well, I've now got my top and my bottom. So my top is going to be 3x times 3x, so that's 9x squared, times that by 2, so plus 9x squared, plus another 9x squared, just to be clear, but or 18x squared straight away. But then you've also got a hole in the top, which is x squared by x squared, and I've got 2 of them, so take away 2x squared straight away. And then the bit that everybody can't always forgets, I almost forgot it, there's a surface inside this tube as well, so I need to work out what that surface is. Well, there's going to be 4 of them, and it's just going to be x times h. So plus 4xh. tidying all that up a little bit, my area is 12xh plus 4xh. That's just my first and my last one. And then my x squared is 9, 18 minus 2 is 16x squared. Or my area is 16xh plus 16x squared. If you can get that far, you're getting a mark. But we're not finished there because our area in the question's not got any h in it. So we need to work out if we can eliminate that h somehow. And let's look at the information. The volume is 2000. Well, volume is length times breadth times height. So if I write that down underneath, volume is length times breadth times height. Volume of the big box, which is 3x times 3x, which is 9x squared times h. So 9x squared h, but we need to remember to take away the whole, which is x by h. So that's just x squared h. So our volume, 8x squared h, but that equals 2000, it says. So I can now eliminate h from my area by rearranging this equation to make h the subject. So that means that h equals 2000 divided by 8x squared. A mark for getting h. Now we just need to substitute it into a. So our a is 16x times h, 2000 over 8x squared. And we've got still plus 16x squared. Using a calculator, 16 times 2000 divided by a is 4000. So we get 4000 on the top. And we've got cancellation to do, x on the top, so x squared becomes x. So we get x on the bottom, plus 16x squared, or writing it in exactly the same way we wanted, 16x squared plus 4000 over x, which is just exactly the same as what I've just already got. And there's your third and final mark. Part B said, to minimize the cost of production, the surface area A of the box should be as small as possible. Find the minimum value of A. Minimum value optimization. Let's jump straight in. So part B, I want to optimize the area. To differentiate a function, we need to get it ready. So let's start with our area. We've got 16x squared, but I'm going to have to take that 4000 x to the minus 1, so I can differentiate it. And you'll actually get a mark straight away there for getting it ready. We now differentiate it, so a dash or a dash x, 2 16s is 32x minus 4000 x to the minus 2. And that's me differentiated it for a mark as well. So 2 marks out of 6 so far. Now if we fix that by making it equal to 0 because we're optimizing. So remember, stationary points occur when a dash x, I'll call it, equals 0. So we can say 32x minus 4000 x to the minus 2 equals 0. For realizing we had to do that and find stationary points, we get another mark. And then we need to solve it. We'll get another mark in a moment for solving it, but I'll show you all the working you need for solving it. So we've got 32x equals 4000 over x squared, we could say, x to the minus 2. So multiplying through by x squared, we get 32x cubed equals 4000. Dividing through by 32, 125. So x is the cube root of 125. There's only one answer to that. It is 5. So we now know that x is 5 is our turning point. But we need to prove and show that that is a minimum. We don't know if it's a minimum or a maximum. So we need to do a table of signs. So let's do our table of signs just to show that. X going along 5, and we're going along. A dash x, so a number less than 5, but not 0, because 0 is undefined. Then if you picked 1, say, you would get 32 minus 4000 over 1. That's a negative. So we've got negative 0. Hoping that after 5 is positive, but you can check. just get yourself a calculator, pick a number close to 5, let's pick 60, 32 times 6 is 192, 4,000 divided by 36 is 11, that minus 11 is positive, so we can say it's positive, so our shape is down, along and up, therefore x equals 5 minimizes a. So to get a, remember x equal to 5, we work out our area equals 16 times 5 squared plus 4,000 over 5, 1,200 for your final mark. A note on table of signs here. Technically, this is one of those ones where the function is discontinuous. In other words, at 0, because if you can't divide by 0, it breaks. You have to make sure that you have kind of shown that it's in the neighbourhood of 5. I always draw an arrow because the SQL take it to mean a number close to 5, a number close to 5 on either side. If you do that and don't actually say any numbers, you will. SQL High Maths 2021, Paper 2, Question 9. A cylindrical tin of beans has a volume of 450. The radius of the tin is r and the height is h. The net of the tin is shown in the diagram here. So the surface area is given by this formula. So surface area of this, we can use the net. We're going to have pi r squared for this circle, pi r squared for this circle. Now you imagine you've got a tin and it's been unfolded. The whole length of this tin will just be pi times the diameter of the circumference of the tin. So we can take a note of that. That's going to be pi times diameter. And then that is just going to be the height of the tin. Now notice in our formula, as usual, there's no h in here, so we're going to have to rearrange for h, but that's okay because it tells us the volume of the tin is 450. So starting off with that volume, well, let's start off with our area first. So we know our surface area is pi r squared plus pi r squared. Let's just write that down. Plus, and there's no diameter, so 2 pi r instead of pi d, 2 pi r times h. Or to make that neater, pi r squared plus pi r squared is 2 pi r squared. So we've already got the start bit. And then we've got plus 2 pi r h. Obviously that h is going to disappear because looking at the volume of the tin, the volume is pi r squared h because it is a cylinder. And that equals a number which is 450. So we can rearrange this equation to make h a subject. Just dividing through 450 over pi r squared is the height. So we can then sub it into here to make 2 pi r squared plus 2 pi r times 450 over pi r squared. And therefore, finally, we get 2 pi r squared. 2 times 450 is 900. You'll notice that you've got pi over pi, that disappears. R over r squared, so that's just over r as required. Now, don't worry if you can do all that. Notice this is worth 3 marks, but the next bit's worth 6 marks. And it says, determine the radius that will minimise the surface area. Minimisation is optimisation. Optimisation, stationary points. Stationary points occur when the derivative is equal to 0. So for part B, stationary points occur when the derivative, I'll just put a dash r, the derivative of a with respect to the radius equals 0. So the derivative of a, the area, well, we've got 2 pi r squared plus 900 over r. So that's 2 2s are 4. Pi is just a number, r is the thing, the variable. Take 1 away from the power, so that's just 1. Now 900 over r is 900 r to the minus 1. So that is minus 900 r, and then take away 1 minus 2. And we're going to make that equal to 0. We've got a little equation to solve. 4 pi r minus 900 over r squared equals 0. Making a common denominator of r squared, we've got 4 pi r cubed minus 900 equals 0. So 0 times r squared equals this. So 4 pi r cubed minus 900 equals 0. So 4 pi r cubed equals 900. Dividing through by 4, you get pi r cubed equals 225. So r cubed is equal to 225 over pi. And r obviously then is the cube root of 225 over pi, which you can just use a calculator for and get 4.15 centimetres. So we know that r is 4.15, but we need to check if it's a max or a min. So we draw our nature table. So we're going to go along to 4.15 and then along the derivative, a dash, and then the shape. There's our derivative way back up here. So just picking a number before 4.15, maybe 1. You get 4 pi minus 900. Well, that's clearly negative. And then picking a big number like 10, you get 40 pi minus, well, 900 divided by 10 squares 100. So 900 divided by 100 is 9. So you get 40 pi minus 9. That's clearly positive. Use a calculator for any of this. So our shape is down, along, and up. And therefore, r equals 4.15 is a minimum. Notice it didn't ask you to work out the area, so we're just working out the radius, so we're done there. We'll be fine. Question 8. A rectangular plot consists of a rectangular pond surrounded by a path. The length and breadth for x and y, and the path is 1.5 metres wide at the pond ends and 1 metre on the other sides, as shown. The total area of the pond and the path is 150. Show that the area of the pond is given by this equation. Well, we know the total area all the way around is x times y, or y times x. So we know, first of all, for part A to start with, that the area, total area y times x must equal 150, because it says so in the question, 150 square metres. If we go back up to the diagram, this distance here is going to be x minus 1.5 and 1.5, so 3. Similarly, going along the way, that distance there is going to be y minus, and you've got 1 and 1, so 2. So clearly the area of the pond part is y minus 2 times x minus 3. So the area of our pond, y minus 2 times x minus 3. We'll call that A. Now notice there's y in here, but our question doesn't have any y's, but we know that y times x equals 150, so putting that back up there, y is 150 over x. Keep that in mind because we can substitute that in for y later on. Let's multiply our brackets out here. A equals yx or xy minus 3y minus 2x plus 6. Substituting our y in, which is 150 over x, we get 150 over x times x minus 3, 150 over x minus 2x plus 6. So that simplifies to 150 minus 450 over x minus 2x plus 6. So 150 plus 6 is 156 minus 2x minus 450 over x. That's now a function of x. And that's exactly as required. So we've done part A. Part B, determine the maximum area of a pond. This is called an optimisation question. So in this case, we need to differentiate it and find the stationary points. So A dash x, we're going to have minus 2. And if I take a little note up here, minus 450 over x is minus 450 x to the minus 1. So we've got minus 2, then plus 450 x to the minus 2. Or, in other words, a dash x is minus 2 plus 450 over x squared. Clearly x cannot equal 0. So max or min stationary points we're looking for. So we want to set a dash x equal to 0. So that gives us minus 2 plus 450 over x squared equals 0. So multiplying through by x squared to eliminate the fraction, we get minus 2x squared plus 450 is 0. So 2x squared equals 450. X squared is 225. And therefore x is the square root of 225, which gives us two answers, plus or minus 15. X squared equals 225, so x equals 15. We can discount the negative value based on the question and do a nature table for just x equal to 15. So we've got x up to 15 and then at before 15. So at 15 we have got it being 0. If we pick a value before 15 but not 0, as you know, then you will see that you'll have 450 over 1, take away 2, which is positive. And if you pick a number after 15, let's just pick a massive number, 100. If we did 450 over 100 squared, that'd be a very small number. Take away 2, it's going to be a negative answer. So it's negative. So the max area, A of x, was equal to 156 minus 2x minus 450 over x. So at 15, we get 156 minus 2 times 15 minus 450 over 15. That's 156 minus 30 minus 30 again, which is 96. So meters squared. Maths 2023 paper 2 question 14. The net of an open box is shown. The base is 3x by 2x with a height of h. Find the area of a net in terms of h and x. So for part 1, we've got 3x times 2x for this bit here. And then this will be 2x because it's just going to go up the side with that. So that's 2x. And obviously this is 2x as well. We've got 3x here. And then if you just imagine that over the top or around the front, this will also be 3x. So you've got 3, 4, 5, 6, 7, 8, 9, 10. So it's plus h times 10x. So that gives you 6x squared plus 10hx. And it's only worth 1 mark, so there we are. Part 2, given the area is 7,200 centimeters squared, so the volume is given by this. Well, volume of a cuboid is area of the base times the height. Well, the base is this bit here, which we already know is 6x squared. So that's 6x squared h. But that's got h in it, so we need to get rid of that h. But we already know that 6x squared plus 10hx equals 7,200 from the question. So we can rearrange that to find h. So 10hx is 7,200 over 6x squared. So h is, so 10hx is 7,200 minus 6x squared. So h is 7,200 minus 6x squared all over 10x. So now our volume is just going to be 6x squared times the whole of that. I've not simplified that yet because I'll just simplify at the end. So 7,200 minus 6x squared over 10x. So that means our volume equals, well, dividing through by 10 first, I think, we'll get 6x squared, 720 over x minus 3/5 of x. So what I've done there, divided this by 10, so it's still over x, and then dividing this by 2, you get 3/5. X squared over x is just x. So now I can expand the bracket. 6 times 720 is actually 4320. Use a calculator, so you get 4320. X squared over x is just x. And then 6 times 3 is 18 over 5. We'll just leave it like that. Yep, minus 18 over 5. And we get x cubed. Part B, determine the value of x, which maximises the volume of the box. So it's maximise, optimise. Let's go. So for part B, to maximise the box, we need to examine the stationary points. So stationary points occur when the derivative equals 0. So v dash, well, as a function of x, I suppose, is equal to 4320. And that's going to be minus 18 times 3 over 5 x squared. So v dash x is 4320. 3 times 18, 3 tens are 30, 3 eighths is 24, so that's 54. So minus 54 over 5 x squared, and we're going to make that equal to 0. So we can say that 54 over 5x squared equals 4320, just like that, taking that over to the other side. So times them by 5 and dividing by 54, I'll do that. So actually 54x squared equals 5 times 4320, which is 21600. So x squared is the square root of, divided by 54 is 400. So x is the square root of 400, which is equal to 20. Now just have a little note on this. It's actually equal to minus 20 as well, but you can't have a negative length, so it's only 20 the one we're picking. So it's just 20 we're looking at. Now we just need to check, is that a max or is that a min? So x along to 20 and along, examining the derivative to see if it's a max or a min. Okay, so we need to examine before and after 20. So let's try a number before 20. So let's try 19. 19 squared times 54 divided by 5. That number is smaller than this number, so that minus that is positive. So it's positive before 20. It's 0 at 20. Then if you try 21, the same idea. 21 squared times 54 divided by 5 is bigger than 4320. So 4320 minus that is negative. And therefore, we've just worked out that x equals 20 is a maximum turning point. So the box is maximized by x equals 20. Is it centimeters? Yeah. Centimeter. Now we move on to what I would say is unusual differentiation questions. The first one we're going to look at, just stuff that doesn't come up as often, is this one. A quadratic function is defined on a set of real numbers. This was 2017, paper 1, question 15. Diagram 1 shows the graph of y equals f of x with the turning point at 2, 3. And diagram 2 over here shows the graph of h of x, and the turning point is now 7, 6. Okay, let's see what it's asking us to do. Part A. Given that h of x is f of x plus a plus b, write down the values of a and b. So in other words, it's a graph transformation question for part A. So let's have a look to see what's happened. If we look at this point 3, well, let's just look at the turning point. 2, 3. It's clearly moved along to become 7. 2's become 7. It's moved to the right by 5. So if it's moved to the right, then a must be negative. So a is negative 5 because it's moved to the right by 5. And then our b, well, plus b on the end means it's moved. The whole thing's moved up by some number. We started at 3 and we've ended up at 6. 3 plus 3 is 6. So b is simply the number 3. And we're done there. So part B says it is known that the integral between 1 and 3 of f of x is 4. What is the value between 8 and 6 of h of x? Well, an integral means an area. So we know that the area under this bit here is 4. So that means over in this graph, since it's just moved up, this whole area here is also 4. And leaving the extra bit between 6 and 8 is just a rectangle. That is 2 along. And that must be 3 because the graph's moved up by 3. 2 times 3 equals 6. So our integral between 8 and 6 of h of x is just 6 plus 4, which equals 10. And we're done there. Part C says, given that f-1 equals 6, what's h-8? f-1 equals 6. Let's just use a different colour pen now. That means that the gradient of the tangent at this point here equals 6. And it's asking us, what is the gradient of the tangent at 8? Well, at 8 on h of x, 8 is this bit here. Now that's, if we imagine looking at this graph instead, that would be this point here. It's a mirror of this, so it's sloping down the way. So it's just minus 6, because it's just the other side of the graph. So h dash of 8 equals minus 6, and we're done there. Unusual question, SQ Higher Maths 2018, paper 1, question 15. A cubic function is defined as a set of real numbers. X plus 4 is a factor, x equals 2 is a root, f dash minus 2 equals 0, and f dash x is greater than 0 when the graph crosses the y-axis. X plus 4 is a factor means that x equals minus 4 is a root. That's where it crosses the x-axis. X equals 2 is a repeated root, which means that it's also a turning point on the x-axis. That's what happens when you've got a repeated root. So we can start drawing a graph. We can look at the other options in a minute. But if we draw a y and x-axis, just a quick sketch, we've got minus 4 as one of our roots, and we've got 2 is, I'll just put it here actually, as another root. And when looking at our derivatives, f dash of minus 2 equals 0. So we now know that at minus 2 at some point, we've got a turning point as well, not on the x-axis, but then we also know that f dash x is greater than 0 when it crosses the y-axis. So we know that it's going up at this point, but this is a turning point, so it must drop back down. So we now know that it must go like this. And we know that this is a turning point, so it must turn here and go up here because that's a root. So we've got a root, a repeated root, and we're done there. This has been Claire Maths, and today we've looked at the whole of differentiation in the SQA Higher Maths exams for 2023. Take care, stay safe, and goodbye. This has been Claire Maths. Today we went through the whole of differentiation in Higher Maths. We went through every single possible thing. I've taught you the whole thing in depth, and we went through every single past paper question that exists for differentiation. Hope you found that useful. If you did, give it a like and a subscribe. Take care, stay safe, and goodbye.